I'll try contacting one of the people in the room. So often there's someone who is monitoring the audio, who is running the conference AV. If you're listening to the audio, please know that none of us online can hear the speaker's audio input. So I'm just hoping someone from the AV team is watching the live stream right now. Acting some people, so we'll see. Oh, say on-site room.
Whereas now we're moving towards the compile once everywhere approach, which allows us to be like more flexible and more extensible much faster. How is this achieved? So we were like struggling. So like one of the reasons like restricted C was C because of the safety. Like BPF has to be safe. And in this case, not only safe, it has to be like portable. So we couldn't really stay within the boundaries of what C language allows us to do. And we started extending it. So the whole compile once, run everywhere concept and relies on the way we compile the programs. And in this case, this was our first extension to the C language. We added an attribute that called preserve access index. And when you compile a code, a structure that's marked like this, compiler, in this case, like LLVM and GCC, I don't think GCC supports it, but the LLVM, it makes the field accesses, instead of like fixed offset, it makes them symbolic accesses. And this is a generic concept. It's not necessarily like applicable to BPF. So this extension actually works. Well, no, it doesn't work for x86, but it's done through the front end. So there is a little bit of plumbing necessary on the backend side. But in general, it's a new concept in the C language. It's a true C extension that makes the structure layout dynamic. And that's what allows this core as a concept to even work. Then we didn't stop there. We figured that, well, the C language will benefit from things like type information. You can roughly compare it to the RTTI in C++ and other languages, but here it's built in. And again, this is done through the extensions to the language technically, where we can say, we can just ask, like, what's the type ID of the, let's say, struct the skbuff inside the kernel. And we can use this type to actually print the structures, this example of snprintf. We can ask what's the size of the structure, in this case, like task struct. What's interesting here, that the type size macro, it will be resolved at the load time, not at the compilation. At compilation, we'll just wrap the whole stuff in a special things in a relocation. It's a combination between like object files, but I won't go into too much details there. But the language is being extended as a combination of the compiler and the runtime, with things like size of the structure, whether type even exists in the kernel. They all determined at the load time. It all feels so far like I'm not connecting to the exact use cases, but this is just like examples of how the language is being extended. Then we extended it with the key configs. Comparing to kernel modules, like kernel modules can have access to kernel configuration as well. Here, the difference that things like what is the current hertz that this particular running kernel has as a definition, or what's a Linux kernel version of that, will be again determined at the load time, not the compilation time. So at compilation time, the program can be just like compiled once, and then depending on the box, it will get adjusted while being loaded. Then we did even more fun stuff. We've extended C language with a sort of like exception throw concept, but here like the C language doesn't have the catch statement, but it can throw, and the throw will be like automatically mitigated. In the C, it does look like this SKB reference of def pointer and then accessing another field. It will look in the generated code, it will be still a single load instructions that later will be converted into like load instruction plus two branches by the JITs in the kernel. And in addition, there will be so-called exception tables automatically generated and given to the kernel. So when there is actually like a fault, when the kernel doesn't have this address like accessing null or something, like it, instead of like faulting and crashing the kernel, it will just gently will return 0, and this is how the whole thing like works. So it roughly equivalent to the copy probeat kernel accesses and the kernel, but done as an inline function. So not even function, it's just like a single load plus a few branches. So it's pretty fast. Then there are other interesting pieces in the C language. There is so-called type and declaration tagging that we added. And for example, if the kernel is compiled with Clang today, the __ user, if you like worked on the kernel in the past, user and per CPU tags that will be on the types, they were meaningful only for sparse static checker in the past. Now they're actually used for real. When Clang compiles the whole kernel, these types will go all the way through the dwarf, eventually in BTF and in BTF, and will stay there. So when the fire sees it, it actually can enforce the right access. If it's marked user, it will only be like through the probe read user helpers. Now we're getting into somewhat crazy territory. We're now extending C language with the concept of the operator new from the C++, where we add in a type enforced allocation of the objects. We're not like in the normal C, of course, you have malloc. In the C++, you have like operator new that like allocates memory, and this memory can be essentially like void star. It's up to the compiler, but you can have like typecast and then access something you allocate it completely different. In the BPF land with this like C extensions, we will be allocating objects that only of specific type. Like this kptr new will return this foo, and you can only access it as a foo. You can like in C typecast it to a different object, but during the load time, verifier will prevent this access. So it's all in the name of the safety. And the concept, and we also already introduced the concept of the kptr, which is a kernel pointer. There are like two different kptr and kptr reference. They're somewhat similar to the unique pointers in C++, and I forgot how the concept is called in Rust. But essentially the idea that only one entity, like there's only one sort of thread owns the pointer, and you can like atomically exchange it in and out of the maps, and different CPUs can, like, because there's only one ownership, like they don't need to like do any kind of lock-in when they access the object because they're only owners of this stuff. So what it allows to do is, for example, to do maps with a variable length arrays and like store strings, for example, like allocate a string, store it somewhere, then use it later. So this is like all super exciting and very new. The latest things that are also like in the works right now, we're adding the concept of the statically checked locks to the language, and things like linked list and arbitraries, with the goal of being able to construct pretty complex data structures and all inside the programs. In the past, that was unthinkable, I would say. When the BPF was just created, it was the maps were used as a combination of both like allocator and data structure. Here we're separating allocator as a small individual building blocks, then linked list as the simplest like building block as well, with arbitraries and everything else that is coming. So the programmers won't be limited to like a basic data structures, but it will be a lot more powerful. Another thing that we're considering is to have the concept of the assertions in the language. So what we found that like that's probably like #1 complaint that people say about BPF, that the verifier is too dumb. Like I'm writing the program and it's like, it's obvious that, well, I know what I'm doing. It has to understand it, but well, computers are not perfect. So we're going to introduce the assertions, and in the first place, they will help this combination of the compiler, user, and the verifier. When the user can say, well, because I wrote this program this way, like in this particular example, like assert within will tell me, I'm telling the verifier and the whole like BPF subsystem that my word pointer is within this range, so it is like, and if it is not, then please abort this program as a whole thing, because this should never happen. So it's very similar to assertions in like normal user space in C, where you just like core dump and shouldn't happen. But here it's sort of in between helping the verifier on one side to understand that this next like read modify write operation is safe, is within the bounds. And the second time it's like moving. So anyway, we'll see. It's really definitely going to be like fun to implement because it involves unwinding the stack safely and like calling all of the destructors. And this, I just showed you how we'll have the operator new, so there will be destructors that we call during this. But at the end, hopefully it will look like this. So yeah, this I think I already mentioned. So like just a normal example of the typecast. You can typecast in C or C++, and well, the things might crash, or do like double free. It's not okay in BPF. So this is when people say, well, it is restricted C. Yes, it is restricted C, but it's restricted for the purpose of being safe. Okay, so this is a comparison where we were like 8 years ago, what they call the early days of BPF, and today. And I think there were some interesting threads where people were saying, well, what is really BPF? Like what's and I think it's still not clear to many where we stand, whether BPF has a stable API or what's unstable part of it, like how it can affect the kernel, how it, whether like what is actually happening. So this slide is supposed to answer it. In early days, we were thinking as BPF as a system that similar to what we knew before, like classic BPF, where you have a stable instruction set and the API. There is like a protocol between kernel and user space that kernel promises not to break. And this is how extended BPF was done as well. That's why this whole concept of the context and return values, we made them stable. We promised that they're stable. We maintain this backward compatibility through this UAPI BPF.h. And this is we still maintain, of course. What we realized that this is actually not enough, for example, for tracing. Tracing, like it needs to look into inside the kernel and in other cases. So like in the modern day BPF, like we have sleepable and non-sleepable. Now we have, instead of single context, we have multiple. The functions can see the types. The verifier will do the type matching. Then extensions to the, like hooks are no longer like done as hooks. Stable hooks, like the last ones, I think we added were like some on the networking side that was C group based stuff. Now we don't do them anymore. Why? Because we can connect the kernel with BPF in an unstable ways through just adding an empty function. It's like an empty no inline function can be removed, and we did it. So like we have examples where we what's already in the tree is connection between like BPF and connection tracker. And over the last like release, we already changed how this functions look like and what BPF where it can attach sort of and what it can get called. And we're working on what they call here is scattered like knob 5 is the ability to put this hooks anywhere, not only at the beginning of a function, but anywhere. And the way it like look in assembly is just like a knob where there is nothing else but the knob there. And BPF will be able to just like put stuff in there, collect everything in a nice way and get out. So like here it's on one side, some of the BPF programs, especially this old classic sort of networking, like Catran layer 4 load balancer I showed you earlier, looks more like this user space-like, whereas different kinds of BPF program, they're really more similar to the kernel modules, where they have like unstable, where they're tightly integrated with the kernel, they read everything, they see the whole kernel, and they pretty much can call into a bunch of things. So since I was talking so much about kernel modules, like it's obvious that they are not safe. They're not really portable. This whole DKMS stuff is, well, compiler and a host from security reasons, it's not great. And what sometimes people say, well, BPF is such like programs blobs, but like looking at comparing them to the kernel modules are really the blobs. Like they're binary, like there is pretty much like zero visibility in terms of what they do. Whereas like this modern day BPF programs, they're pretty much like kernel modules, but they're safe and portable. And portability is not guaranteed, as I was saying, but we provided tools to make them portable, to make them easier to be portable between different kernels. So this compile once everywhere concept and this preserve access index feature, where compilation makes the symbolic accesses, this just allows and type dynamic checking of the type allows the programs to be written in a portable way, but they are not guaranteed to be so. And of course, like unlike the kernel module, the whole thing is way more debuggable because the types are always built in. Like people can just like look at what all the maps contain based on the name of the fields and so on and so forth. And we also embed the source code in the binary, like by default and unconditional. And it's possible to like really, it's kind of hard to even remove this too. So like when you compile any program, your code will be there. And the conscious choice that we decided to do is like this new kind of BPF programs, it's always GPL only. Like in the kernel space, for the kernel modules, you have export symbol GPL versus export symbol. Whereas here we're just saying the K-funcs, what they call the kernel functions. This is whitelisted helpers, kind of, that BPF programs can call. So all of them are equivalent to export symbol GPL only. So I hope some of these examples made you think, well, I hope I convinced you that this BPF-C is the better choice as a language for programming and developing the kernel. But the part that was, I think, like, is still that I think actually Benjamin probably will explain better in his presentation that coming right after. But the way we're trying to develop aiming for the BPF system to work is to make it a tool out of it, something that any other subsystem can use without actually like sending emails to like BPF mailing list and talking to us. Like if there is anything in the verifier, we'll help you to add it. I think we've added everything that the HID subsystem wants on the verifier side. So now it's up to human interface devices to define how they can use BPF. And same applies to like any other subsystem. I think last night I saw somebody like from Google sending patches to use BPF in multi-generational RU or something like this, where it was like also like no BPF, no core BPF changes, but another subsystem like would be able to like become more like programmable with the help of BPF. And then this other subsystem can decide whether they will stay like completely this kernel dependent, or they want to provide some sort of API like guarantees, at least like not breaking. So now it will be a choice of the subsystem whether it will be like stable or not. And with this, I'm done and I'm out of time. Thank you.
Benjamin, there's a question. Hi, Ted Cho. So I'm curious whether you've had any thoughts about how do we manage user expectations about whether a particular BPF program is supposed to be more like a modern BPF where it's like a kernel module, there is no portability guarantees whatsoever, or classic eBPF where it's more like user space and there is a better guarantee of compatibility between kernel versions. Because, you know, we can make this policy statement, it makes sense to me, but how do we make sure that users of eBPF programs understand this distinction?
Right, so yeah, excellent question. So we were not, yes, documentation is definitely like our weak point, that's for sure. And like what we discussed, we're going to document in this UAPI BPF.h which program type is like old style or the new ones, because it is the case already today. Like when people doing like XZP style program, it is this more user space with a guaranteed API. Whereas like all of the programs that are like proc type tracing, LSM programs like included, they're really this on the right side. And they actually like don't really, there is no like program type that in the both camp. So it's really binary when you look at the program types there. And for the new BPF programs, we're not going to be adding most likely any more program types. So it will be hopefully much more obvious what it is today. Right now, unfortunately, it's like, yeah, without documentation, it's hard to tell unless you like really know involved in the BPF, but it's pretty binary.
So the recommendation I'd make is documentation is great for developers. For end users, it might be interesting to think about, are there ways you can work with the package managers so the package advertises, what the compatibility guarantees are, right?
Even
so
package like
yeah, I mean, what I'm saying is it's more about the communication outbound to end users, not just documentation, right? Both are important, yeah. But if end users start complaining that eBPF, this particular eBPF package that has been, shipped by Red Hat Enterprise Linux all over the world is no longer, backwards compatible, and they complain to Linus, it would be nice if there was a way to point that, people missed all of the signs that said this is a kernel module thing, not a user space thing, right? So it's documentation is important, but I'd encourage folks to think beyond that, just to avoid confusion, right? You need to over communicate.
So I think this is an interesting thing that Ted brought up, right? Like if packages in Linux start shipping with eBPF programs, now they are already, and they know this way where you can reverse chronologically, like add BPF programs. And since the logic is shipping with the application, it is much easier to do than with kernel modules.
You preach into the choir.
But like we need to write this down on how to roll out. The project Leaf was one example where this could be laid out properly, that this is how you load, but other areas we should document or
Yep. I think there was a few more questions here, and we're probably last question since we're really out of time.
Okay, you mentioned very briefly statically checked locks. What's statically checked about them?
Yes.
What are you checking?
That's a long topic. Yes, like it's absolutely it's still work in progress. But we think we know how to do the statically checked logs. We actually have both static and dynamic, but I can spend half an hour just talking about it. So let's definitely talk about it more, but probably like offline. And I'm of course available for everyone. I'm here all 4 days, so catch me in the hallway.
If you can validate the locking that exists in the code, you could theoretically automatically generate locking as well.
Sorry.
So if you had like some attributes that say, okay, this data type is protected by this lock, the verifier could automatically generate the locking.
Yes. Yeah, that's exactly what we're going for. Like we'll have the lock and like roughly the concept. Like we'll have the concept of allocation, where lock and the stuff like linked list, arbitrary or fields, they come together as part of single allocation. But the single allocation, a single like kptr new is a new operation. So the lock and the fields that it protects to, they come together. And because of this, like we know what is guarded by what, but in some cases we cannot. So we'll have the type tagging, kind of type tagging, like using the Jekyll and type tagging extensions that we added to C to use that to say that this field is actually protected by this lock, or this linked list is protected by this lock. Then the verifier can enforce all of this static.
Yeah, that would be great. All right, thank you very much, Alexei. We owe a lot of gratitude towards you. Okay, now we'll have our next talk. Benjamin's going to talk about HID-BPF. All right, just begin.
Thank you very much. So yeah, I'm Benjamin Tissoir. Most of you must not know me, I guess, because I'm working in a different subsystem than BPF. But I work for Red Hat. I'm the HID co-maintainer, and I'm going to talk about HID-BPF. So as a forward, this is still a work in progress. It's still not included into mainstream kernel. I got the V10 for the HID port that has been submitted, but currently I'm targeting 6.2 because now we sorted out all of the BPF core changes that I wanted to have it. The API is mostly designed, but as I was focusing on the BPF changes, I'm still missing a few bits to have the full extent of what I want to have in HID-BPF. So what is HID-BPF? It's HID plus BPF, of course. So I'm going to talk first a little bit about HID to explain to you why, what it is. I'm going to skip the BPF part because I suppose that you all know that and you just got the presentation from Alexei. Then I'm going to explain why this is important to have HID-BPF in my opinion, what it is from a user point of view, and how it was implemented quickly. So HID is a plug-and-play protocol. It stands for Human Interface Devices. It's a very old protocol from the Windows 95 era for handling plug-and-play USB devices, mostly your keyboards and your mouse. If you brought your just brand new Windows 95 computer, you've got a diskette with it, a floppy disk, and you have to actually install the driver with the keyboard that you just bought. So there is a chicken and egg problem, so they created this plug-and-play stuff. We've got a lot of various different transport layers now. And the nice thing is that most devices are nowadays working with generic drivers. And for that, they rely on HID report descriptors. I'm going to quickly dive into the report descriptors because I'm going to use that quite often. But what you have to know is two things. Is that the first thing is that it describes how the device talks in a very simple language. There are no loops, no conditionals whatsoever. And it's static for each device. It's stored in Flash, and if you look at any device, HID device that you have, it tells you you have one, basically. So on this one, for instance, I've got a mouse that is exported as a pointer, so it's a cursor on the screen. I've got a 5-bit for the 5 buttons, then I've got X, Y, and so on and so forth. So it's very, very simple, and it's just a static block in the device. If you want to go further with the HID stack, I've got two documents for you. The device class definition. What's important here is that it's a very old document, basically. It's 20 years ago. You've got the explanation of how do you parse the report descriptor, all this kind of stuff. But mostly the HID protocol in itself has been very stable for the last 20 years, which is good. On the other hand, you've got the usage table that you can have, who are actually defining the various usages within the report descriptors. So for instance, X and Y are the generic desktop pages as 0x30 and 0x31. It is continuously extended by companies. The most disruptive change were the multi-touch protocol, I think. The USI pen was interesting. The hardware sensors also in all of the laptops was quite fun to have. But what's important is that most of the time, except for a few exceptions that I just listed above, an update means new hash-defined the kernel, so it's not too bad. So what's the problem with HID is that most devices are working with generic drivers, except for a few, of course. Half of the drivers that we have in the HID subsystem need a fix-up in the report descriptor. So the small blob that you have in your device is wrong, or we don't know how to parse it, and so we have to fix it. Most of these drivers are under 100 line of code, which means that they're really small, and some of them are just changing the input mapping of one key, for instance. So I was attending kernel recipes in Paris for a few editions, and I was all the time seeing those people talking about eBPF, how eBPF was great for tracing and for analyzing the kernel, and I was like, I believe there is something that we can do with it, but I was not able to find it, and now I'm happy to say that I actually found it. And so I'm going to present HID-BPF, which is basically use BPF in HID drivers to have user space driver fixes in the kernel. So the basic principles of HID-BPF is that in the same way on the network's stack, you are working on an array of bytes and you are processing it. In HID, we are also processing an array of bytes, and we are talking HID. We've got HID on the input, HID on the output. We don't have any access to any other subsystem, otherwise it would be a mess. And my goal is to have any smart processing done in user space or at compile time, or at programming time at least. So if you want to parse the HID report descriptor that I shown previously, you do it into user space, and then you just inject the small bits that you need into the HID BPF program. If you want to compute location of the various fields, you also have to do it in the at programming time. The difference between HID-BPF and generic BPF is that we are actually targeting a specific device for a given program. We can't fix all mice in the same way because they are using different protocol, different languages, and so we have to decide which program goes to which device. And last, as Alexei mentioned, our HID-BPF program has to be GPL. And the idea that we have is to ship the fixes of the device directly in tree. So why do I need HID-BPF? I've got 4 use cases, and let's dig into the first one first, which is having a more convenient way to do simple fixes and user testing. So today, if a user has an issue with a key on his keyboard, for instance, first we have to identify the issue. Then we have to create a new patch and write some tests for it. The user needs to recompile the kernel, which is kind of difficult for most of the users. Then we have to submit it to the LKML, and we have to do the review of the patch. Then there are changes into the patch, and we also have to ask the user to recompile the patch to be sure that we actually tested the last version of the patch and this is kind of like ROI for the user. Then we include it in a branch, the patch goes into Linux tree, the kernel is marked stable, the distributions are taking the new patch, and the user can drop the custom kernel build, finally. So during most of the cycle, we are asking user to lock their kernel version to a given version, and they can't have CVE fixes unless they recompile their kernel, which they would likely not do. And they won't be able to tackle other bugs in other subsystems because some other subsystem might have a different root of their tree. So in my opinion, that's a problem. So what I want to do with BPF is I want to, instead of writing a patch, I want to write a BPF program. And I can also compile it directly on my developer machine, and I can just forward the source and the object and ask the user to just drop the object into the file system. When I'm talking about BPF program, I'm not talking about something that is very fancy. I'm just taking the input stream. So in that particular case, I'm taking the report descriptor, and I'm just fixing 1 byte within the report descriptor. And most of the time, this is just enough to fix the device. The interesting point is that the user implication will stop here once the BPF program is accepted. The user doesn't need to lock its kernel version to continue to do all of this roaring stuff like recompiling the kernel. But then the developers are continuing to include and ship the fix within the kernel. So that's the end of this first use case. So the second use case I have is the HID firewall, which is something that I would like to implement quite quickly, mostly because of an application that is named Steamed. Because the for many reasons, for many good reasons, they decided they want to directly talk to the devices through HID-BPF. And so given that there is no login D support for it, what they do is they tag the device with UAccess, which means any program on the session can actually talk to the device, which is fine in most cases. Like SDL is quite happy with that too, because they are doing the same. But the problem is there might be a bad actor coming in, and they want to do a controller firmware upgrade over the network through a Chrome plugin, which is something you can do. And basically, you just brought your brand new PlayStation 5 controller for, I can't remember the exact price of it, but it's quite pricey. And somebody might actually break it and transform it into a paperweight. So that's probably not good. With BPF, what we have is that we've got an overview of the entire kernel, who is accessing what. And so we can say, okay, let's allow Steam to directly talk to the device. SDL is also, or actually anybody who is doing read-only access can have access to the device if it's part of the session. But if somebody tries to access the controller update endpoint on the device, we just refuse unless it's called firmware update. The other thing that might be interesting to do is to be able to change the device based on the user context. The example is from the Microsoft Surface Dial. I've got it. I can make some demo for the people in the room if you want later. Basically, this is a very nice looking rotating knob with a push button on it and some haptic feedback. You've got some clicks whenever you turn it. And from the kernel point of view, it's exported as a rotating knob with haptic feedback, except that nobody in the user space uses it. The reason is simply because the developers in the user space don't have it. They don't see the interest in having it. And so basically, we are exporting that device and nobody uses it, which is a pain. So what you can do, however, is if you look at the usage, whenever you're in a browser, you can say, okay, I would like to use it to scroll the page with a very high resolution, and so I can finely tune the scrolling. This is possible, but I would not have to have this device turned into a mouse to do that, because the browser knows how to use a mouse and a scroll wheel. But what if I'm on a menu that I popped up or like something? Maybe I want to have a lower resolution, but some haptic feedback when I'm ticking between the various elements in the menu. So the thing now is that the behavior of the device depends on the context. And up to now, what we had to do was to simply, add a new kernel API, add a user space that deals with that custom kernel API, and require some weird convoluted way of, okay, now turn the haptic feedback on, turn the resolution on and off, all this kind of stuff. And we don't have any we don't know if this user space application is there. While if we say, okay, you're the application, you're in charge of that device, and you can turn it as you want, that's much simpler in my opinion. And last but not least, tracing. In HID, we are lucky enough that we've got HID-BPF, which is very easy to have a look at the devices and what they are saying. The problem that it's good, but it's not good enough because we just see it's a one-to-one communication between the device and the application talking to HID-BPF, which means that we don't know when somebody else is accessing the device. Which is why suddenly you receive, okay, this was an answer to a question, but I don't know what was the question. With BPF, we can trace external requests, which means that we can actually debug, okay, well, there is an application accessing my device in a wrong way, so that's not supposed to happen. Okay, so what is HID-BPF from a user point of view? The first thing I'm going to explain is the net-like capability, which is you've got an input stream of data coming either from the device, which is kind of like the network stuff, and you output something else. So as this is built on top of BPF, this is a tracing BPF program. This is not a HID BPF specific program. It's a tracing BPF program with the F moderate. So you can actually change the return value of the program, which gives us the ability to filter out entirely the event. I already mentioned the HID-BPF get data over there, which gives you the ability to actually get the input stream, the current input stream, and it's a read-write input array of bytes, and you can do whatever you want on it. If you want to invert coordinates, or if you want to remove or reshuffle the bytes, you're free to do. And the interesting bit also, I think, is that this is executed before any other driver processing, even before HID-RO. So from the HID subsystem, everything happens as if we just receive the fixed bytes from the device, but from the rest of the driver, it's like, yeah, we don't see it. I mentioned previously that we wanted to be able to attach one BPF program to a device. This is done with a HID-BPF function, which is called HID-BPF attach prog, where you can actually say you uniquely identify a HID device, and you use the program FD of your BPF program, and you can actually attach it. There are some mechanism inside. I'll go back later on that. But this is done by user space or by the kernel space once it's implemented. And of course, you can add more than one program per HID device, which is interesting because if you want to have the HID firewall, the fix-up, and the tracer, you can have all of them together attached to the same device, and you can have all of these working happily together. The ordering of execution is, of course, an implementation detail, and I don't want to have any guarantee on it. You have a flag that says, okay, I want this program to be first, but if somebody else comes later that says, I want this program to be first, then the other one won. So what are the benefits of this? You can easily filter out unwanted field in a stream of an input device. Like if you've got a very old joystick that has some drifts, you can actually say, okay, let's enhance the neutral zone of the joystick. If you have an old mouse also, that gives you spurious button clicks. Currently, we are filtering them out in user space, but we could also do that directly into the kernel space. We can fix the report when something should not happen. Some devices like to send events that are completely unrelated to what we are actually doing. You can just filter them out or change them. And you can change the device language to morph the surface dial or the rotating knob into a mouse. So how do you do for that? You use the RDesk fix-up, report descriptor fix-up. Basically, this time, HID-BPF get data contains the report descriptor of the device. You do whatever you want on this array of bytes, and you just return 0. And whenever you attach this program to the device, there is a disconnect reconnect of the device, which means that the user space knows that there is a new device appearing, and it just works. And of course, for sanity reasons, there can be only one program of this type per HID device. So if you try to load another report descriptor fix-up, then it would just fail to load because the first one was already pinned. What does it mean to have the report descriptor fix-up? You can fix a bogus report descriptor. If a key is not properly mapped, you can morph the device into something else, or you can change the device language, which is cool. Okay, and of course, sometimes you want to talk to the device. Are my LEDs lit up? Or you want to actually light up some of the LEDs or set the haptic feedback or whatever. And for that, we've got the HID-BPF hour request. And because this is inheriting the HID hour request function of the kernel, it cannot be used in interrupt context, which means that we are not in a tracing program, we are in a syscall program this time. So it's completely from the user space to in the user space context to do that, which allows you to query and put the device into a specific mode. From a testing user perspective, I played with a work in progress at this URL. It's a simple daemon written in Rust that just waits for the UDEV event, and whenever you plug a device, it just takes the mod alias and looks for any BPF object that has been previously compiled. And if there is a match, it would load the BPF object. And if within the BPF object there is a probe syscall, it would run that probe and check if the program applies to the device. And if not, then it would just keep the BPF program. And unplug, of course. If you unplug the device, all of the non-HID-BPF programs are detached. The interesting bit is that with just that small piece of code, I already have a proof of concept that you can just ship to users a BPF object, and they can just put it into the file system, and whenever they plug their device, it works, it fixes. So that's great, in my opinion. The next thing that we have to do is working at shipping the fixes directly into the kernel. It's still to be discussed, in my opinion. I've got several options. I don't have a strong preference for any of them, so I'm open to any suggestions. Of course, I prefer having BPF object as a proper kernel module, but let's not rush to that point. So the first three technical solutions are either I automatically create one kernel module per source file that is dropped into the kernel tree, which means that we're going to have a lot of various kernel modules just for those fixes, because it's one per device, which is maybe not. We could also ship the kernel sources into the kernel tree, but provide the blobs as into the firmware tree. And so the user space would just have, we use the same loader, either where the blob is coming from the firmware tree or from a developer. Or we could also have one gigantic module that contains all of the eBPF programs. That would be whenever we load a device, we just load that module, see if there is any match, and then unload the module. Don't know. Okay, so quickly how this was implemented. The first bit is that HID-BPF is built on top of BPF, but completely outside of it. I think Alexei made it clear in his presentation that he wanted to separate subsystem from BPF core. And this is how you would do it. Basically, if you want to add a trace point within your subsystem, you have to rely on the allow error injection API, simply to be able to have F-moderate tracing programs. Which means that the developer is actually in control of where you want to put your trace points in your code. And so, which means that you can also have some guarantees that you won't change the function parameters or all this kind of stuff in the future, because you explicitly know that this bit is the BPF hook. The next thing is the kfunc. So basically, a kfunc is exporting a given kernel function as an eBPF dynamic API, which means that from the other subsystem point of view, we don't need to update eBPF whenever we are doing a change, and it's completely dynamic to the current kernel that you are building. However, I would like to mention that care needs to be taken because it's in the end it's very much like a syscall, except to the part that eBPF takes all the cumbersome part away. You don't need to have to worry about argument checking because, or even if the code is available or not, because the verifier will tell you, well, no, you're using that program wrong. The versioning is kind of also in the same way, because like if you add new arguments, you can say you can reject, thanks to the verifier, the old programs if you want. And this was possible because of all of these BPF changes that I did and that Alexei merged last week. Thank you a lot for that. For the custom handling of BPF program to device matching, it's a fun piece of code in the HID-BPF code through a BPF program that is loaded that handles a map of BPF program, which is, yeah, interesting. But the rest are already there for the BPF core port. So I included a few changes for like being able to have kfuncs for syscall and tracing, I think. We know from within the kernel more control of the BPF maps, which is good. You've got also better access of context in syscall. That one was quite difficult to get in, which means that now within syscall you can use the context as an array of bytes if you need to. And last but not least, kfuncs can now export a read-only or read-write array of bytes. So to wrap up, in my opinion, should simplify easy fixes in the future. We should allow to add user-space-defined behavior depending on the context. You can add traces in the events. We can have live fix of the device without having to update the kernel, which is very important as a Red Hat employee, because I can ship that without having to upgrade the kernel. And as a maintainer, I would be able to have no more custom kernel APIs for things that are actually just for one active user specification. And of course, it will definitely not replace regular kernel module developments for the vast majority of things. And that's the end. So if you have any questions.
So what I usually do, and I know a lot of other people do, is this thing called control escape, where you use single key for escape and control. If you like press and release, it generates escape. If you press control and some other key, it generates control something. I use custom firmware for now. Will this thing eventually allow me to drop it and implement this in BPF?
Hopefully, yes. The one thing that in the PID study it's not there completely is that you cannot generate events from the syscall, but it's just a kfunc away, basically, because we are in there. But yeah, the idea is to have like these software macros keys that are directly handled by the kernel, so you don't have to wake up user space for that.
Awesome. Yeah, thank you.
The get data, I assume it's kfunc, right? Like HID-BPF get data, like on slide 42. Did you look at DIN pointer? Because it seems like it's doing exactly what DIN pointer is supposed to do.
You mean the input array?
So if you can switch to slide 42.
Which one?
42, 42.
42? 42? Oh.
42, yes.
42, yeah, but 42. I mean, I'm going to give it 41 slides.
It's 50. It says 56 right now. So like if you can switch back like 10 slides or so. So you have this BPF HID get data, right? Where you specify offset and size, and then you get the pointer to data.
Okay.
So that seems like that's what DIN pointer, if you've been following the BPF development recently, is like sort of interface. So I was wondering if you can just use like generic functionality for that.
So when I first worked on that, it was I think it was slightly before, or at least the key pointer thing was in development, so it was not available. But the thing, as far as I understand from kpointer, is that you're actually asking BPF program to allocate data?
No, not kpointer. It's DIN pointer, dynamic pointer. It's generic, not typed, just like exposing the array of bytes, basically. So that's exactly what you do here. Maybe. We can talk about that afterwards. Yes. But yeah, all right. But like as it is right now, that's kfuncs, right? HID-BPF get data. Is it kfunc?
It's a kfunc, yes.
Okay.
Do we have time for a question from the chat room?
I think so, if you want to.
Yes. From the chat room, Agata asks, do you have any fun or cheap or both USB HID devices to recommend for getting started with hacking?
Sorry. Do you have fun devices to start working on that?
Basically, are there any USB HID devices that are kind of cheap to acquire, but that are good to hack on, is what Agata wants to know, I think.
Basically, you don't. I mean, as long as you've got a mouse, you can work with that. It's not. You don't need to have like this fancy Surface Dial. It's just use a mouse and that's it. But you need to have to wait for that to be in the mainstream kind of.
Cool.
Okay.
Thank you very much.
Thank you.
Okay.
Hi, good morning. Can you hear me? Cool. All right, I'm all set on my end.
Next, we'll have Barrett talking about eBPF kernel scheduling with Ghost. Please begin.
Good morning, everybody. Today, Barrett from Google, eBPF kernel scheduling with Ghost. First, I'll go over a little primer about what Ghost is and how it works with Ghost, and how we extended it to do all BPF only scheduling. So, as a reminder from our talk from last year at LPC, the Ghost is a kernel scheduling class. It's below CFS and priority. Our kernel decisions, our scheduling decisions are made in user space by an agent process. The kernel sends messages to the agent, such as task X walks on CPU 6, and the agent issues transactions to the kernel, such as run task X on CPU 12. Sorry about that. Can you all hear me now? I think I was muted. Let's see. How about now? Okay, I think I saw a hand wave in the audience. Okay, great, thank you. So the kernel's in blue. That's where our scheduling class is, and the messages go from the kernel to the agent, and that transactions come from the agent back to the kernel. Overall, the Ghost motto is to do no harm. Using Ghost should not hurt the operating system, and we want to have our agent faults be isolated. So even during operation, Ghost doesn't hurt the rest of the system. We run below CFS and priority, and CFS will preempt Ghost tasks is what that means. This also includes kernel threads. We're not going to schedule those or stop those or anything like that. Similarly, if the agent fails, all of our tasks get moved back to CFS. And what failure means is configurable and triggerable by user space. So one thing we have, for instance, is if the kernel notices a runnable task doesn't run for X milliseconds, that'll be a failure. Similarly, a user space daemon can notice errors or poor performance, or the application can, and then basically just kill Ghost from user space. You can also have multiple agents per machine. The Ghost Sched class supports distinct independent agents. And we have this abstraction called an enclave. It's a set of CPUs scheduled by a single agent. And you can move CPUs between the enclaves. And there's even a live update mechanism where you can hand off control of an enclave. Let's talk a little bit how BPF works in Ghost, since this is the BPF track. The agent attaches processes, or BPF programs. And we think of the BPF as an extension of the agent. It's these red boxes here, still part of the agent. Messages are now the BPF Ghost message send, which we refer to just as BPF MSG. And transactions are another program type, Sched PNT, which is pick next task in the scheduler lingo. And here we have the decisions are still made in user space, and BPF itself is just kind of hooking into the messaging and the transactioning layers. And this is where we were about a year or so ago. In a little bit more detail, there are specific contexts for both of the message types, but essentially BPF message is just the message. Task 6 woke up, and PNT is basically, hey, who runs next? There's even more detail. We actually have a lot of messages, both messages about tasks and messages about CPUs. So you could actually picture the life cycle of a task through, hey, it was new, it blocked, it woke up, etc. Similarly, we have a bunch of things on the CPUs. Like the obvious one is the timer tick. Did a timer tick expire or not? And there's other ones related to like the operation of Ghost and the agents. And the thing that's interesting about this is that these are the message types that are getting sent to the agent, but you don't actually have to deliver a message. These are more like a functional API. So like the BPF message really is just a giant switch statement that processes each of these. The BPF programs, we added a few of our helpers, things like wake up our agent. Probably the most important one is the second one, which is run the GTID. That is basically run the next task on the CPU. And we can do things like reschedule a CPU. Essentially, it's setting the need resched bit, and ultimately, like an IPI and whatnot. I want to emphasize that these programs are part of the agent. I think of them as acting as an agent thread with basically the same privileges as the user space agent. And they're embedded in the agent binary, just like with like LibBPF applications do. And they have the same lifetime as the agent. They share the memory with the agent as well, in the sense that we use giant map type arrays, and the map are from user space. And I jokingly call this ring B or BPF space because it's all of the analogies to x86's ring 3. You have your array maps are windows into the address space, and you have your helpers are your entry points of the kernel, etc. So that was where we were before. And where we're at now is we have our BPF only scheduling, where all the scheduling decisions are made in BPF. And user space still has a role, but not in a critical path. So everything in red is still the agent, but now the decision is actually made in BPF itself. And the agent communicates with BPF maps, both to user space agents as well as to the application itself. And from the kernel's perspective, nothing has changed. We still have the same interface of messaging and transactions. And why do we want to schedule in BPF? Well, we actually have alternatives with Ghost. One is we could context switch to that CPU's agent task and handle messages and pick next task from user space. Well, the obvious reason is that there's no context switches, and similarly, you don't have to actually kick a task off a CPU to run an agent. Just the example of a task of waking up, I don't want to have to preempt another task just to tell the agent about task 6 waking up. From the perspective of a scheduler writer, though, the BPF is synchronous. This really solves a lot of my heartache. For instance, when I run the BPF message program, we're actually holding the run queue lock. And for pick next task, we're actually in the middle of scheduler pick next task. One of the things about the user space programming of Ghost agents is that you're always acting on old data. There's a message that came for you a while ago, but you're asynchronous, you're not holding any locks, you don't really know what's going on anymore. We have mechanisms to deal with that, but it's a little bit harder to worry about and program around. Of course, there are downsides to programming in BPF. Your limited loops and all the other stuff that everyone knows about dealing with the verifier. The other thing is it is a little bit harder to do stuff like spawn background threads. Like one of the things we do in our user space agents is just, I just kick off a bunch of CFS threads to do work for me. It's a little bit more convenient in user space. And data structures are somewhat limited to BPF map types. I know there's a lot of new stuff with the key pointer and whatnot. So we'll see where that goes. But it's still a little bit harder than user space at the current moment. We'll talk about BIF, which is our simple BPF only scheduler. And it's basically the world's simplest agent. It's a global FIFO scheduling policy. We have just a run queue, which is a BPF map type queue. And here's actually what the early version looked like. In picnics task, all I did was pop an element and then called the helper to run the next thread. Similarly, BPF message send, I mentioned earlier, it's just a giant switch statement. Well, the only messages I cared about were wake ups, preemptions, and yields. And if so, I had a runnable task, stick it onto the queue, and exit. Now, the thing is, you want a little bit more than that for any scheduler. So you got to have error handling, and I really wanted to have some accounting helpers and stuff like that, because really any non-trivial scheduler is going to want to have to track per CPU and per thread data. So the BPF code is more of a policy-less tutorial for how you can track data and share it with user space and an application. So we have a few different map types. The one is the CPU data map type is a per CPU. But it's actually not a per CPU map. It is a giant array that is indexed by CPU. The reason for that is I want to be able to map it from user space. So I have my map type array. Similarly, we have this thing, the per task data. It's called the SW data field. SW stands for status word, which is a ghost thing, but it's basically a dense array of structs. And you can have whatever you want in the struct. I have, like, what time did a task wake up? When did it last run? You can put whatever you want in there. And this thing is actually indexed by the status word index, which is basically it's a densely allocated integer for every task in the ghost system. And you want to find your index. So we also have a helper lookup table, which is a map type hash. But essentially what you have in the end is two mappable arrays by both user space and by the application. And they have all the info you would want for your scheduler, whether it's like the per CPU data for what's your current task, or just your per task data. The other thing is very cool is you can actually pass these file descriptors over socket to an application so that they can tell us their per workload hints. Here's a couple examples of actual BPF code. There's little helpers that I've thrown in there. Stuff like, hey, if a task stopped, what is the basic accounting I would like to do? And it's just kind of a simple example of, you look up the elements, you can set whatever field you want. And similarly, we have a helper to kick a CPU to do a resched. But just kind of basic C code. And here's actually one of our message handlers. This is how I do the wake up. I've got this dirty no inline and casting games for the main function itself. That's just boilerplate what I had to do. But as far as what do you do on a wake up? Well, find your per thread structure, do some accounting, and then stick it into the FIFO map. One of the things that's interesting is you'll see a lot of spots here where it's like, well, if I didn't actually have the thread struct, well, then I'd fail to enqueue the task. That would actually be a serious problem because now a task got lost by the agent. One of the things that from the earlier talk, the first talk in the session, I talked about the assertions. This little get if no SWD, that should never happen. I would like to, if I could replace that with an assertion, and that way, if this does fail, it would fail very loudly. Now, I made a comment earlier about having that handle wake up no inline. Well, apparently, I get some horrendous error from the verifier about dereference of modified context pointer. Just for reference, what the context looks like is a union of a bunch of actually of every message type. And from my end, I needed to trick the compiler to not do something or other with a register, and that's fine. I don't understand why exactly that happened, but to me, this is one of the sharp edges of working with BPF and the verifier. And I tricked it to make it compile properly, but every so often, little things like that pop up for me. Talk a little bit about our future work. Next thing we want to do is actually implement the CFS algorithm in BPF. This is the default Linux scheduler. And there's actually a bunch of reasons to do this. The first is BPF was a stupid scheduler, but is it possible to implement complex scheduling policies in BPF? Or for instance, am I going to run into like weird loop limitations, or do I need new map types that I haven't thought of yet? Similarly, what are the changes needed in Ghost? Right now, I've got the picnic task and the message hooks. Do I need more hooks added or a different interface entirely? from the researcher aspect, there's also the thing I call the ghost tax. That's the performance overhead of all the ghost mechanisms. If I have the same policy as in kernel CFS, I could do an apples to apples comparison to say, well, here's Ghost's performance with CFS and here's in kernel CFS. That delta should be the cost of using Ghost. We actually do a CFS in Ghost user space as well, and then we could see all three. There's like kernel CFS, BPF CFS, and then user space CFS, and get an accurate measurement of what is the cost of these extensions. Other cool things you could do is you could actually tweak CFS if we have our own implementation beyond the existing sysfs settings. And you can even do that for a subset of CPUs or even particular applications. One of the things I was looking at is, we're probably going to need a new map type for a priority queue or heap, for instance, an RB tree. And I saw Dave's work on that, so that's great. I figured, yeah, you probably couldn't just use the existing BPF map helpers, but the stuff that's going on that will be great for us. One of the other map types I was thinking of, and I haven't seen anyone doing this yet, but maybe that the bin pointer is the thing I'm looking for. But I was looking for something like a pre-existing memory blob. For instance, all the maps I've seen so far were allocated by the kernel, but if I wanted to look at a blob of memory that came from somewhere else, whether it's like device memory or something. But yeah, that based on the comments from the previous talk, maybe I can look into the dynamic pointer stuff. But ultimately, I just want to treat something like an array map that I know what it is and be able to access it. A couple discussion points. One of the things I was wondering about is that, Ghost itself has its own user space ABI for talking to user space agents. And can we implement that purely in BPF? For instance, we have the status word table is a thing. It's a dense map of thread data. It's similar to the one that I create for the BIF scheduler. The kernel itself, the Ghost kernel, actually maintains its own table like that. I think that's the sort of thing we could replace purely with BPF. Similarly, I mentioned at the very beginning that Ghost works by sending messages from the kernel to the user space. We actually have our own power of 2 ring buffer, the standard thing that one would implement. They are basically very similar to BPF ring buffers plus our wake agent helper. So we could actually replace our messaging infrastructure, at least the user space side of it, with BPF. There's a couple things that are a little harder to do in BPF. I mentioned the agent itself has tasks on every CPU, and those are very special in the kernel. There's like special kernel code for it. They actually run above CFS, and there's a couple other little things. So I'm not really sure how easily we could replace the whole notion of an agent task with BPF. One of the other points I want to mention, and I mentioned this a little bit earlier, is that our user space agents are asynchronous. The BPF messaging and the Ghost infrastructure we have for that actually can handle that. And it's because all of our messages have sequence numbers, which are passed back to the kernel whenever you show a transaction. And this really is the thing that makes sure user space is acting on the current state of a task. So if we were to replace any of our Ghost user space ABIs, we would basically still need something like the messaging. So for instance, if I were to throw away our Ghost channels and our status word table and stuff, we would still probably want to keep our sequence numbers and have that be something that is passed to BPF. Even though Ghost BPF doesn't use the sequence numbers too much, it's still something we would want, knowing that there's going to be a user space agent, at least the potential for a user space agent out there. And the other question is that pops up is Ghost right for other BPF only scheduling frameworks? There are a couple other people we've been chatting with from like Facebook and whatnot who are also interested in having their own BPF only scheduler. And I do think that Ghost probably could implement those other ones, or those other ones could be implemented on top of Ghost. I want to make there's a distinction between our sched class and the user agent ABI. So like the internals of how Ghost works and hooks into the scheduler can be used for a lot of things. And it just so happens that our user space ABI is just one thing that we've decided to hook into that. Another way to put it is that BPF message stuff I mentioned earlier, it's not actually messages that get sent to user space. It is more of the API from the kernel calling into BPF. As I said, it's a giant switch statement. And as a technical matter, you could have like the dispatcher tables and other stuff, or you have separate program types for every one of the messages. There's a bunch of things you can do, but the main point is that these are the things you can expect to hear from the kernel if you're a BPF program. And the thing we were looking to do is extend that to make sure that we have all of the attach points and APIs and then I guess upcalls really that that other frameworks might need. For instance, one of the things that Ghost has helped with, at least from my head, is that you still want the BPF messaging interface, because Ghost has sort of figured out all of the really horrendous corner cases. For instance, the message task we generate in 7 different places. And because there's a lot of nuances about when threads change classes, was it on CPU, was it about the block? There's a bunch of things that, and maybe some of those are problems of our own creation, but from the perspective of a scheduler writer, what I want to hear about is just one time when a task wakes up, and one time when is a task new happen. I don't want to have to figure out all those spots on my own. And to some extent, we also think that Ghost solved the issue of safely delegating scheduling to some other agent, whether it's user space or BPF, whether it's synchronous or asynchronous, or at least we are aiming to solve that issue. But so yeah, I think other schedulers frameworks could probably be built on top of Ghost relatively easily. So the main points I got is that Ghost is this relatively safe, extensible kernel scheduling, whether it's in user space or in BPF space. And you can do just purely BPF scheduling. You can also do user space scheduling. You can do a hybrid scheduler, all sorts of stuff. And we've got an example of scheduler called BIF. It's just a very basic policy, but it's sort of an example of how you could make your own scheduler. And there's stuff on the roadmap of CFS and more advanced schedulers, different map types and stuff like that. We do have some rough code up on the Ghost kernel and Ghost user space repos on GitHub. It does lag our in-house changes, and sorry about that. And yeah, we also got to use Basel to build the libraries for now. Sorry about that too, but I'll try to get some other C code out there that can be built with just a makefile. And if you have other questions, I have a long list of frequently asked questions in here. I'll do just one because I know everybody always asks about what is the BPF task local storage. That is this task storage get. One thing I want to point out is that in blue, that task struct task pointer, for the most part, Ghost doesn't really have visibility in kernel data structures. A lot of the BPF, from what I've seen, kind of lives on a spectrum of are you very close to the kernel or are you closer to user space? And based on Alexi's talk earlier, it sounds like the modern BPF is very, very close to the kernel if you're talking about replacing kernel modules and whatnot. The Ghost BPF is more on the user space side, where I think of BPF more of an extension of user space in the way we're using it. So, for instance, Ghost BPF doesn't have visibility into these data structures. We could give them that, but yet we have the compile launch run everywhere. But for the most part, the contexts and everything else, that's all ABI structs. We don't even use the task pointer for anything. We just have the task ID. And finally, as far as I know, task storage isn't accessible to user space. So that's kind of why we have our own other business. At this point, pretty much out of time, so I'll take a few questions. But if you're curious, the slide deck has many more frequently asked questions, mostly about scheduler internals and stuff like that. But and I see a question in the chat, and then I guess we could also take questions from the on-site room. I'll read the first question from the chat. Was from Quentin. Historically, scheduler maintainers have been rather opposed to using modules in the scheduler. What's the plan to overcome that problem with Ghost? Is using BPF going to make it easier or harder compared to a proper kernel module? That's a good question. I think the plan would be to get together with a couple other groups that are also interested in using BPF scheduling in the scheduler. Let's see, come up with probably the union of all the things that we need, or find like a framework that works for all of our use cases, and then see if we can use that to convince scheduler maintainers that this is worth doing. But so far, I've mostly been talking with large scale companies doing things that are like on large scale servers, like Facebook / Meta and stuff. But yeah, it'd be also interesting to see if we can get people from the Android community or somebody like that who also have the desire to tweak the scheduler in certain ways. I think BPF probably would make it easier than a proper kernel module, but that's always hard. That's always hard to say. But I feel like the safety arguments of BPF is something, especially as part of the whole Ghost thing too, is that we want to be able to convince people that this is relatively safe. I don't think anyone will trust a kernel module, but having having BPF and like the verifier in our pocket might help with the argument. Let's see. I got another question from Brendan. What is a key example to What is a key example to explain the need for Ghost? Let's see. A primary one is that we have applications that are high-value applications that want custom scheduling, and with CFS, a lot of times you'll have even with the nice levels, like the priority settings, it won't necessarily run the thread you want at the exact time. There's a lot of little rules. Like for instance, one that pops up is if a thread gets on CPU, it won't get kicked off for X microseconds. And then another thread that is behind it may be extremely important to an application, but it won't run at that moment because of that. We have a paper that I think it was about a year or two ago now that goes into more details on some of this stuff and has some various workloads where we work on. Let's see. I think we did a deadline scheduler in user space. So when a thread woke up, we could get onto CPU quicker, and typically you'll do things like tail latency is a big one, stuff like that. Let's see. So those are the questions I had from the chat. I don't know if there's any questions in the room. Your room is muted too, which I think was to help prevent the feedback we were getting early on. So if there's any other questions, take them now. Oh, I can hear you now. A little quiet.
Okay, so I was going to ask about the storage gap as well, even though you had it or not. So you do have map.
Sorry, I heard a little bit there. I was trying to mute myself to avoid getting any feedback from you all. Yeah, sorry, I think you all are muted again. Alternatively, if someone could type the question in, that might help.
I think the task of storage does have an SD-based interface, so you can access it by you need to grab a PDF of the task you want to handle, and then you can update tasks of the storage use case as well. So, and then you will also follow with the I think I don't know whether you can have tasks of the storage stuff, but probably. The other question I have is, so then you mentioned that the upstream scheduler maintainers are a little bit reluctant. So is this course going to be a shared class in itself, and then what is the plan for upstream that shared class? Are we in engagement with the scheduler maintainers? to the BPF side is mostly it's dependent on that shared class.
Sorry, this is a little frustrating. I'm having a hard time understanding you. Yeah.
So we have to, Barrett, we have to either talk here or you talking. So now we'll mute and you talk.
Okay. I could hear you very clearly when you said something right there, but I could not hear the question very clearly. I'll mute now.
So, Barrett, the question is that this Ghost, the predicate for any Ghost support in the upstream kernel is dependent on that shed class that needs to exist there. So, is there any plan to upstream that shed class so that there can be some BPF-based extensions to that? How far those conversations are, and are we discussing them at Plumbers here?
Let's see. So yeah, definitely agree. We need to have some sched class, whether that's Ghost or one of the other ones that are out there. It's not gone very far. We do have open source code, but not upstreamed code. And I think there are a couple of people floating around Plumbers talking. I've heard that Peter Z isn't physically there, so that I'm also physically not there. So that's we do have a couple other people from the Ghost team and from Google around there. But yeah, part of the reason I wanted to give this talk was to get people aware of the stuff that we're doing, so that those talks can go on either at LPC or offline, or on mailing lists and whatnot. But yeah, definitely agree. We need to have something in the kernel already to hook it in. And the thing we want to do is make sure that whatever goes in works for not only us, but for whoever else has similar needs for their application. For instance, I had those lists of all the message types we've been dealing with. Maybe there's different messages that other people need, or maybe we've got too much crap and we need to cut it out. But good question. Thanks.
The question for the room is that can we do a BOF for scheduler? So there is scheduler interest from from Meta folks as well, from Google. And we should be talking to scheduler folks, the scheduler maintainers, as to what their requirements are. Otherwise, this will always remain in as a user space, something separate from the scheduler stuff. Alexei, Daniel, what do you think towards the? Oh, you can't. Okay. Okay, I'll mute this and then I will talk. Hello everyone. I think we're like so first off, we have you can talk about TCP for data center networks.
Enable. Okay. Hi everyone. Today I'm here to talk about tuning the Linux TCP for data center networks. I've heard like 3 really cool eBPF talks in the morning, so I'm glad to start with more like networking focus kind of topic. So this is the outline of my talk. We're going to talk about what the data center network look like and how do we tune for TCP network performance. But equally important, I will talk about how do we tune for the host performance, as well as TCP visibilities for the network. And I'll talk about like the challenges of how TCP can survive in the next decade in the data center networking. But before I start, I want to introduce a little bit about myself. I work in Google for a long time, focusing mostly on the TCP performance for both internet and the data center networking. The work I'm talking about here is actually a collective work by many people, all these Linux NetDev contributors in the Google network infrastructure. So kudos to them for this really cool joint work. And my talk today is not specifically about what we have done at Google, but more or less best practice and experiences in how we tune the TCP performance at Google data center networks. So let's start with the data center networks. The network basically has many hosts interconnect at the Gbps links with less than millisecond latency. And we use the ECMP protocol to load balance for all the flows onto the links. The links obviously are shared by all these hosts. It's not a full mesh, but that's why many hosts have to share the links together. And the application, a typical workload is a scatter-gather. And that's why you have correlated bursts from many hosts at the same time. So many flows sharing the links, competing with each other. And the applications care about latency and CPU and memory resources. So it's important you strike the balance among all these metrics. And because of this sort of application workload mapping to this network topology, then you have actually bottlenecks occur in host and the networks. But usually those are invisible to the applications. Applications, when they start the communication operation, they see everything underneath as the network code. So for us to really tune the TCP performance, the application usage is really critical for us to profile and know where to go to optimize TCP. Let's start with the data center application. The topology, the data center topology, not the application. So basically you have all the hosts that's connected to a top of rack switch, which is the green little button there. And then they, again, go up one layer and you have all these switches interconnect each other so that it forms a basic 3-tier CLOS topology. But the way to think is that essentially it's not a full mesh network. And the application, in order for hosts to talk to each other, you often have to traverse up and down, sharing the links with other hosts in order to communicate freely among many different hosts. And a typical host, usually a server, has many thousands to millions of TCP flows at the same time. They are not always active. You can think the application basically multiplex all these messages across them constantly. That means for a particular TCP flow, a lot of times it's idle and then burst and then idle. And the application just spread all these messages on these flows. So the way to think is, it's not a bulk transfer that goes for a long time. It's like periodic burst, and the flow usually lives a long time, but it also idles for a lot of time. But it's many, many flows competing at the bottlenecks at the same time. So how do we optimize TCP network performance in this setting? Ideally, what you want is you want to maximize the bandwidth utilization across all these links available provided to you with the minimum queue, because you don't want to build the network queues. If anything, you want to use the congestion control so that you move the queue from the network to the host. And at the host level, when the queue is built at the host level, then you can selectively prioritize which message to send next. Instead of if the queuing is happening in the network, there isn't much thing you can do because the switch is just going to forward them in a relatively FIFO order. And that's the idea, to use a good congestion control, which we will recommend use ECTCP or the BBRB2 congestion control. They both utilize the ECN signals, so you do have to turn that on. But you can immediately improve this kind of minimizing the queue while maximizing the bandwidth situation, because the default congestion control cubic, the way the principle, the way it works is you try to shuffle packets into the network as fast as possible until the queue blows up and will cause losses. But by that time, there is just too much queuing in the network, and you would rather keep the queuing at the host. So in addition to that, what you want to do is you want to minimize the restart overhead, meaning that you want to keep persistent connections and prefer just reduce any kind of setup overhead. For example, you can use the TCP fast open that put data in the SIM to even reduce one round trip to start your applications. And equally important is this default setting that the TCP has, is that if you leave a TCP connection idle, it would every RTO reduce the congestion window by half. So if it idles for just a few milliseconds, that's long enough for the congestion window to reduce all the way to the default value. And you do want to disable that, because that means you kind of like restart the probing all the time. And because you idle a lot, that means you essentially are restarting with a default CWIN, which is not ideal. But there is a side effect to that, is that, well, instead of restarting at the initial CWIN, you are starting with the last non-CWIN, which can be a full window burst. So if you imagine that there is 1 million flows all bursting at the full window, and that could indeed cause severe congestion. And the best way to mitigate that, we found, is that you want to introduce TCP pacing here. So instead of doing a direct full CWIN burst, you want to pace them over a round trip of time. And with the FQ, which you mix a lot of different flows together. So while they are traversing in the network, they naturally will leave. So maybe they would leave this interposed sort of a breathing room, so you can mix and match well, so to reduce sort of the burst-induced queue pressure. So both are all very effective that we have used internally at Google. And another feature that we want to we think that are very useful is that for a very, very long time, right? Basically, the way TCP works is you start on a path, and inside the data center, it's pretty much fixated because the routing has sort of programmed out where you need to go. But with some data center have converted to IPv6, there is this really cool thing that you can do, which is called the flow label in the IPv6 header, where you can specify, essentially it's a 20 bits header, that you can use that to indicate sort of the path you want to do. It's different than the source routing, but what we do is we have the switches take this flow label in addition to the 4 tuples to use that to determine what's the next egress port you use. So every time you change the flow label, that means the switch may forward the packet on a different path. So how do we use this thing to sort of repass the TCP dynamically? What we do is, since we know if the TCP flow is experiencing congestion or not from the existing congestion control, we can use that as a hint to change that, the flow label. And we can even use things like round trip timeout, RTOs, to signify that there could be a potential link failure or severe congestion. So what we have done is that we make TCP be able to kind of swiftly change different paths if it detects either a potential link failure or a potential hotspot. So in this picture, what I'm showing is that there is a flow that's traversing a hot link. And then because of TCP congestion control of that flow sense that, then it changed the flow label of the outgoing packets. And then the switch will hash it to a different path. It's not guaranteed to be the sort of the better path. It could be also a hotspot. But if you continue to do that, then the system will start converging, and basically the energy will move from the hotspot to the cooler spots. It's a little bit like you're driving down the highway where you're stuck behind, say, a slow truck. Then basically you was trying to square, you were trying to move lanes in this way to load balance the system itself. This is a feature that we just published in the Seccomp this year called protective load balancing, and we like to upstream the code very soon for DC TCP. It requires almost very small change to TCP in order to achieve this very cool load balancing feature. So it's a dynamic flowlet that we have used and found it very effective. Then I want to talk about the TCP WAN performance because it's actually equally important. In our data center, we do have, say, customers, internet customers, right? Google.com visitors coming into the data center, and these are all WAN performance. And at the same time, you also have some either latency sensitive traffic, let's say some global controller traffic, or throughput sensitive data replication traffic across geographically diverse data centers. So both latency and throughput are pretty important in here. But for WAN, since the round trip time is already high, the first priority is to reduce the round trips because the round trip delay is already high. And you apply the similar technique. You use persistent connections and you disable slow start after idle. And if you do have packet loss, you want to be able to recover that in sort of fast recovery, round trip time at clocked manner, instead of like timeout and then you go through this exponential back off. So we would recommend using the rack TLP, which is already the default in TCP, to maximize the fast recovery. And in order to boost the throughput, what we found out actually the number one issue is that our current Linux default TCP buffer size is usually too small. If you really have very long haul links with GBPS links, for example, from London to Singapore is easily 200 millisecond or higher. And in that case, you need to properly size the TCP buffer and you can already get good performance. And if your WAN links also suffers this kind of bursty losses, when you collide with the local data center burst, you want to use something that's less loss sensitive, like a BBRv2 as well. These are also very effective techniques to ensure the WAN performance. So I've talked about all the network performance, and I'm going to move into sort of the TCP, CPU, and memory efficiency, as we found that are equally important to the applications. And there essentially are many bottlenecks in the host. The obvious ones are the copies between all the send and receive could be extensive for all the IO intensive applications. And the user space and kernel process handling the same socket can be scheduled on different CPUs, and that can cause a lot of overhead as well. And the other ones I mentioned that the current data center applications, it's many flows exchanging small messages. And what you want to do is that you really want to minimize the wake up or the boundary crossing events as much as possible. For example, if you have a remote procedure call, or application data frame or message, right? It's fairly useless to wake up the application to receive only 99% of the data, because all the application is going to do is just to go back to sleep until he receives the remaining data in order to do anything useful. So you rather send him the whole thing instead of, hey, this 99% of the partial frame. And the last one is the, again, system call overhead, when a server suddenly need to write into 10,000 sockets of 3 bytes each. And you want to find an efficient way to do this. An important part is the thread affinity, because we're trying to process the packet on the same CPU where the user threads also runs. Sounds very intuitive and obvious, right? But you want to make sure that you set the core ID of the sockets where the receive message and send message are called. And when you use them to set the core ID on Paul, which we would remove, this heuristic don't work that well without like very careful orchestration, because the scheduler can move the user threads around, and the previous user space threads can get back blocked or pinned and doesn't work for all the processes. So that means you just need to do a lot of careful profilings and look at really the application workload in order to optimize all these different bottlenecks. And what you really want to try to do is you process the TCP events at the same core, both in the user and the kernel. And sometimes this can tie down to really detail of how the particular CPU works and how the cache line works. So here is a simple example, right? Like you have 2 cores and you receive the packets from one side, and then basically you put them in the memory of that core. And then unfortunately, then you need to process them in a different place. Then that's a lot of overhead already to cross these boundaries. And this can go really undetected for the applications. So they have like really little visibility of what's going on. But yet what they see is a high CPU usage, and maybe they have some CPU quotas that would really limit it, their sort of a throughput. So like you can see, that's just one example. For example, another one is that you can have soft RRQs on CPU 0 and the user code on another CPU cycles for extra copy. This could also put a lot of overhead in this particular server. And I think basically what I want to show here is that there could be just like multiple bottlenecks in all these different hosts, and where you would do a lot of profiling in order to resolve them. And it varies among different applications as well. And let me give you a more precise example. For example, some applications that on the send side, it needs to send a lot of data. And essentially from the application to the LPC stack memory, that could be pretty efficient. But the expensive part comes from the RPC stack to the kernel memory, where you do a lot of copy from user. And those is where you need to apply some techniques like a TCP zero copy, which is fully supported in our Linux kernel. But it can come with caveats as well. For example, some of the cache services, right? It would sound like, oh, cache services is the best example to use TCP zero copy. But because it's a cache service, the page actually has a lot of ref count. So in this case, it may not be that sort of a big saving to use zero copy. A regular copy could be actually better than using a zero copy because of the ref count activities on the particular page. Using another example is on the other side. For TCP receive zero copy is that when you have big packets, and those packets can turn into single pages, and you can use the zero copy to really relieve the receive side bottlenecks. And we have found this to be actually more generically available or applicable to most of the applications where the receive side is often the choke points for like, especially like storage servers, for example, that need to receive like a big chunk of data. Then I want to move to more like the TCP telemetry, which we also spend a lot of time on, because again, as I mentioned before, we found that a lot of times you have to profile the application, and you have to let the application know where the choke point is. And before we have to do more features in this area, application usually can make sense of the TCP statistics. And the infrastructure side, the TCP people or the host, the networking people don't have enough data to study application performance, right? Because think of what application sees on the left side typically is, okay, our flow, the TCP flow has some average RTT of 10 milliseconds, and some loss rate, and the average window is 31 packets. This is complete cryptic to the application developers, what those mean. All right, I don't understand what you're talking about. My message is not delivering to the other end quickly enough. Something is missing in between. And that's when we want to really associate all these TCP flow level applications to the individual messages, right? Application data frames. In the Google's case, we primarily use the RPC stack. So we do a lot of this instrumentation at the RPC level. So that we know, okay, for the particular message that you care about, your RTT is this, and your loss rate, you're suffering a high loss rate, so that both sides can start making sense of, is it the network or is it something in between? So let me be more concrete of what we actually do log. Imagine you have a TCP sender who is calling a send message to send some block of data, likely a RPC request or response, right? So at the TCP queuing time, we start recording, okay, what's your current window and sending rate and your retransmission status. Essentially do a snapshot of that particular TCP sockets. And then at the queue disk time, and you cannot do the same. So you know that, okay, once the packet has traversed through the queue disk, again, you snapshot the TCP stats. And you do that again when the TCP ACK acknowledging your entire response has come back. Then you can do a diff of this TCP socket stats, and then you can tell, all right, during this time when we are sending your message, something has changed. Maybe the loss rate, your message encounter very, very high loss rate, for example. And let me show you what we will actually plot to the application is this progressive timelines of, what a message has been experienced and how much time it takes while it's traversing the whole stack on the sender side, on the receiver side. And with all this timestamp, then it's very clear that where are you spending most of your time? And surprisingly, we found that a lot of time, it's not even that middle cloud, the network. The packet or the message was stuck in, say, the queue disk, or stuck in even the RPC channel processing pipeline, because the application suddenly burst 10,000 messages, and it has an artificial limit of how much buffer it has, things like that. Or the application message has been properly, kernel has all processed that, received that, and even acknowledged that in the receiver, yet the application thread is sort of starving to pick up the data. So it's queuing on the receive side for several milliseconds. So this kind of visibility really helps us to analyze individual applications of their choke point. And surprisingly, that network, in my experience, is probably only less than a third of time to blend. A lot of time it's all this queuing in this different stages of the pipeline. So I don't have time to talk about a lot more TCP optimizations that have been done. For the memory isolation, I'll highly recommend you attend the talk tomorrow at 3:45 that by Shaquille on the memory isolation. We have done sort of specific topics in IETF at different over the time, like TCP zero copy, also the big TCP with the bigger TSO GRO to allow 200 Gbps networks. And there are interesting features like TCP silent close, where think of a server suddenly needs to be shut down or need to migrate, and it needs to close hundreds of thousands of connections. And sometimes this SIM flood can actually cause outages of all these clients receiving it. A very interesting incident. And there is also a lot of development on the multi-pass TCP. Also another talk in tomorrow's afternoon, highly recommend. Another tricky issue we found is the default Linux is really, the TCP is really tuned for the internet performance. And that's why the minimum RTO is still 200 milliseconds. This is definitely way too long for data center applications. But you cannot just reduce it, even though today IP route allows you to reduce that. Because if you reduce that to, say, 5 milliseconds, unfortunately, you will retransmit very quickly, for sure. But a lot of times, those could be spurious, because on the other side, the delay arc in Linux TCP is still by default 40 millisecond minimum. So a lot of time, the access delay is not, there's really no loss, but you are just spuriously retransmitting. So this kind of work, we are still going to, we need to upstream our changes to the links in order for everybody to benefit. And then there are also many other cool features. I'll refer you to look into this slide decks. Okay, I think I'll conclude with my talk with that. I think Linux TCP is still a major use sort of a transport vehicle in data centers, even though there's been a lot of this cool new transport technologies coming up with offload and all that. But a lot of part really can be replaced, like Linux TCP, like a congestion control module, and can be continue to optimize with eBPF. And I'll give you some challenge I think that would keep TCP to continue to survive and even maybe dominant in the next 10 years. I think we really need to put more focus on cross-layer optimization, like the application data unit awareness. And now with eBPF, we can really do this in a more generic way. I'll give it another, just a small idea, right? If you think of a TCP and the congestion control window, it's completely by-stream based. It has no concept of application data unit. For example, the congestion window is 10 packets. So he now sends 10 packets, but the application data unit is actually 11 packets. If you can just afford to send one more packet, then the other end can receive the entire data unit and it can immediately process that. But because of TCP is stuck with this packet-based system, you have to wait for another round trip, right? So what if we can really optimize the TCP scheduling to be more application aligned with application data unit? I think that would be really cool. The other is today compared to other transport or kernel bypass transport, I think TCP suffers from small message processing, sending 200 bytes of data. Those can be highly optimized by the other transport, but things like IOU ring provides really a great opportunity. So TCP can be equally as performance as those transport as well. And the last one is extending TCP protocol continue to be not easy because you basically have to get a new option number from eBPF, and that process takes several years. Any smart way to kind of improve that process can really introduce sort of let TCP protocol evolve a lot quicker. So, and that's the conclusion of my talk. I'm happy to take questions. Thank you.
Any questions? Thank you very much for your presentation.
Thank you.
Next, we have David Ahrens that talks about whether this app can be used for very high-speed applications.
All right. Hello. Or maybe a little bit higher. Okay. Hello, everyone. My name is David Ahern. I work for a company called Infabrica, and I'm going to talk about some recent networking experiments that we've done to check out how Linux is scaling. So we started out with this fundamental question: how does the network stack scale as line rate increases? Specifically, we're not focused on the current 100G and 200G that exist today, where you can see that you can't hit 200G line rate for a single flow. We're focused on the next generations, the 400G, the 800G. What does it take to run applications at that scale? And by scale, we're not talking about just scaling out, but scaling up. We want to be able to push a single flow to line rate, things like the machine learning apps, just as much as we want to be able to leverage that line rate across multiple flows on the server, right? So one reason we want to start this now is we have to get out in front on what's needed. If there's anything that's needed to the Linux kernel, as we all know, changes to Linux can take a very long time. In some cases, XDB being the poster child right now, it can take way too long to get very needed performance improvements into the kernel. So let's start now, get in before the hardware is available. So to that end, we created a custom setup to investigate how to push Linux software at higher and higher rates. And when I wrote the abstract back in June, I was able to hit 670 gigabits for a single flow, 31.8 million packets per second, again, for a single flow. Somewhere around end of June, early July, we had hardware failure. Fans went out, had to get the motherboard replaced. The person that takes care of the hardware for us, he made some other changes. And when that box got reinstalled a few weeks ago, I was kind of surprised to see a new limit, 782 gig. So this setup is now coming close to what is 2 generations out for line scale rates. So how did we get there? So we took 2 off-the-shelf servers. These are just custom, these are just standard commodity servers running Ryzen 9 Zen 3 CPUs. 5 gigahertz is the CPU rate, 3200 memory speed, stock OS. We took the 5.11 kernel was our starting point. Then we moved to 5.13 a few months later for some other reasons. The key here is that this is an unmodified kernel. All of our changes are in our code. We didn't make any changes to the Linux code. We're using VCU 1525 FPGAs from Xilinx to have our custom logic to do these tests. Now these cards are PCI Gen 3 by 16 based. 128 is our cap from the PCI perspective. We have 2 100 gig interfaces. So how do we push higher than 200G to do these studies if our physical limits are bounded? When you look at some of these benchmarking apps, they don't really, the payload on these apps is kind of irrelevant. And if it's irrelevant, why send it, right? So let's save that precious bandwidth going over the wire for the things that we care about, and this ability to stress the Linux software stack to see where it's breaking and what's needed to make it go faster. Okay, so what we've done is you got an application running on host A. It does the normal socket setup, the normal receive message, send message kind of calls. It's pushing a message down to the kernel. The TCP stack does its thing, creates some SKBs, and those get pushed down to the driver. The driver looks at SKB, copies the headers into the descriptor, looks at the payload and says, this thing's supposed to have, say, n bytes on it, say 1448 bytes. Puts that amount into the descriptor, drops the payload. The user logic in the FPGA sees that data link and says, this packet's supposed to have a certain amount of bytes onto it. And if it's a TSO packet, it does the right thing in splitting it up and then puts the actual proper payload for that MTU size into the header. So we're snatching the true data length of that packet in the urgent pointer just to make a valid packet that can be routable through a network and getting over to the peer. On the peer side, the user logic in the FPGA sees that urgent pointer set and says, this packet is supposed to have payload on it. Let me tell software about this. So it sets the descriptor, the data length in the descriptor to the value that's supposed to be on that payload. The driver that's managing this FPGA keeps a data queue, right? So it's going to manage a data queue just like every other high-speed NIC out there, right? So when a packet comes in, the hardware's got to land the payload somewhere. Well, in this case, the driver is managing a data queue just like it normally would. And instead of the hardware landing the data, the driver looks at that descriptor and says, I have to come up with X amount of bytes of payload data. Pops the first entry off the data queue, signs that to the SKB frag as pretend data to go up the stack, okay? If it's a larger packet, we just keep popping pages off the data queue until we've given the SKB the amount of data that is supposed to be on that packet when it goes up to the stack, okay? The key here, no modifications to the kernel, all the games to avoid these PCI limits and the physical limits of our network. It's all contained in the bottom end of the driver and the FPGA user logic. Well, anyone who's run any kind of test now, first thing you need to hit is no copy. So get the easy one out of the way, right? I think it's fairly easy to say modern workloads need hardware to land data and application buffers, okay? Excuse me. All right. Linux has zero copy APIs. The TX one is fairly easy to use, but it's got some overhead around pinning pages and reaping completions. The RX zero copy API, it's really constrained. It's not a generic algorithm. It requires a specific MTU. The data has to come in page-sized chunks so that it can do the page flipping. And then there's a sideband with mem copy for anything less than the memory copy, right? So what I did was I modified iPerf 3 to implement the TC zero copy API. That's good enough for these tests to show the intent, which is avoiding the memory copy for every packet that's coming in, going from kernel to user space. The extra cycles around the page pinning and completions, it's a factor. It shows up in the perf reports, but it's not a limiting one. It allows us to do these tests. The ZC API for RX is not usable for this case. So we mimic the intent of it by just dropping the data. So again, using the standard BSD socket API calls, we're setting up the socket, we do a receive message, but we call it with message trunk. And the idea here is that the kernel will tell the application how much data it was going to give it and then drops it. So we avoid the mem copies and we get to do this, you know, if the data was landing in the buffers, everything's working like it was supposed to be and the application's being told what was landed. So the end result here is that we're avoiding the mem copy, but we're still using all the existing APIs. And this allows us to go forward with some of these experiments. Second thing you're going to hit is memory management. I said I was hitting 31.8 million packets per second. That's 31.8 million pages per second that the driver has to keep track of to land those packets, to land things that are coming in for that application, okay? That's a lot of data. First thing you learn is that old school dev-out pages is never gonna work, right? Modern NIC drivers are using the page pool infrastructure. Even more, they have to use their own per CPU page cache on top of page pool to really get the overhead of managing pages down. And the MLX5 driver is an example of this. If I recall correctly, I think the page pool infrastructure now has the per CPU cache going on top of the page pool. The key is that you absolutely cannot go out to any kind of a global allocator. You got to be able to manage things locally, okay? And then the other thing is an SKB. You got to have an SKB for the networking stack, okay? Well, the NAPI cache served a good purpose here. That was a very good optimization that got put in. It allows, again, local recycling of these SKBs to avoid some more overhead. The key point I want to make about memory management, the current buffer management scheme has way too much overhead to be thinking about 400, 800G kind of line rates. The next thing you got to do is amortize that software overhead, okay? You've got to do things like validate the packets coming in. Is it being forwarded? Is it going to delivered locally? Is there an application waiting for this packet, right? So you got to do a socket lookup. There's all these different generic OS infrastructures that have gone in for TC, for NetFilter, for eBPF, all these nice hooks that people use. This is also overhead that every one of these packets trips over, okay? So how do you reduce that the software packet rate that's being gone through? Well, there's two levers for this. Normally, if you ask someone, how do you get increased throughput? They'll say, increase the MTU. But it's kind of a naive response. You can't just jack the MTU to 9100 all over your network, okay? You really got to have a more sensible approach into how you're managing things. The other lever is to do TSO and GRO. And the idea there is that you're pushing your effective MTU. So in other words, the MTU that the software sees, you're pushing that as close to 64 kilobytes as possible. To give a pictorial view of what's happening here, you have an application that's sending a buffer and it goes down in the network stack. And the TCP stack wants to use TSO, for example. And so what it's trying to do is to create an SKB with a payload as close to 64 kilobytes minus 256 as it can, the 256 being for packet headers. But it has some constraints. It wants to create MTU sized packets on the wire, or it wants the hardware to be able to do that. So what it's really doing is setting its TSO goal size to be n times the max segment size so that you're creating these MTU sized packets, okay? Now, this packet goes down the stack, goes to the driver sets it up for the hardware, and the hardware sits there and slices that packet into n MTU sized packets. Those packets hit the wire, they go over to the peer. Hopefully, conceptually, they all arrive in the same coalescing window so that the driver is processing those packets all within the same time window. It allocates an SKB, attaches that page frag to represent the data, sends it up to software stack. The software stack does an analysis, says, oh, looks like these two packets belong to the same flow. I can take the data from the second one, append it to the first one, get rid of that SKB, right? It'll continue to do that for the rest of those other end packets, creating effectively, if everything's gone right, the packet on the RX side looks exactly like the packet that was sent on the TX side. A large payload with the headers on top of that, and that's what goes through the field lookups, the socket lookups, and all the other networking infrastructure hooks. LRO comes along and says, software can't analyze everything. It's going to be too slow. Hardware needs to do this. Hardware needs to identify that all of these packets go together in the same flow. And so then the driver creates one SKB that appends all that data onto that packet so that it takes care of the burden of the overhead in terms of what's got to be done to create the large SKB that goes up the software stack, okay? So with a good LRO algorithm, you can see, or a good, hardware LRO algorithm, you can see how it would compare as you vary the MTU and what you're going to get for your data rates. So adjusting just the MTU only is the bottom line. Using software GRO is the middle line. But it's the hardware LRO that gets you the big speeds, okay? And that dip at 6,800, I will come back to. This shows the packet rates on the wire. Really what it's getting at is it's kind of flat when you start looking at that MTU, which really gets into, you're bounded by how many packets per second the software stack can manage. So one thing I haven't heard people discuss before is this correlation between MTU and TSO. You have to have a good TSO efficiency. And if you make a bad choice in your MTU, your TSO packet size is not what it could be. And so your software has to do more work for the same load, okay? So this is what I'm getting at here. And a prime example is to pick one more towards the 8,000 range. 8,200 MTU in an IPv4 52 byte overhead, it puts 8 segments into a TSO packet. 8,300 can only put 7 segments. And 8,300 MTU is 12% less efficient in that TSO packet size. So you're making software do more work just because you picked the wrong MTU. Right, so the bottom line that I'm trying to get at with all of this is reducing that software packet rate means you have to have a solid LRO algorithm. One that can handle out of order frames, one that can handle multi-flow on the same set of queues. And again, one that's gonna do the work for you so that software doesn't have to do any kind of analysis to see how things can go together to reduce the burden on the software stack going up. All right, continuing to peel back these layers. We've talked about the mem copy, memory management aspects of it, and reducing the software stack. The next one gets into keeping the pipeline primed. You don't want hardware to ever be waiting, hey, I got nothing to do, right? Send me some more data to send. Well, the BSD socket APIs, that's the receive message, send message calls, okay? So when you do a send message by default, iPerf3 defaults to 64 kilobytes. That means every time you call send message, it's only going to kick 64 kilobytes down to the kernel. It's not very efficient. You're doing a lot of system calls to send data. On the other end, you can keep jacking that parameter up and the socket buffers on the kernel side to hold those references, but you do kind of reach this plateau where you're not going to get any more benefit out of shoving more things in a single call. But really, the key point of this is the overhead of using sockets to get data to and from the hardware needs to be improved. There's a lot of overhead there that we gotta get past. I mentioned that dip at 6,800. Well, when I'm doing all these different tests and closing in all these parameters, I honed in on 64 meg for a send message call. That's every time I did a send message, it was sending down 64 meg in a single write. The socket buffers were set to 128 meg, right? And kernel, the Linux kernel doubles that size internally to 256. So that was an interesting little tidbit that at 6,800, there's this huge drop, and it was consistent every single time. The 6,800 MTU capped out around 250 gig. But if I change those parameters to 32 and 64, suddenly that little well shifted somewhere else. Okay. So I think what this is really speaking to, I was going to go down this path of digging into exactly the details of what's going on. That's grains of sand and how the kernel's managing that socket buffer. And that's when the hardware died at the end of June. And I never had time to come back to this. But effectively what I'm getting at with this entire socket buffer syscall thing is we have to have a better system to manage the data path that does not rely on system calls. IOU ring is an example of this. It has user kernel queues where you can set up what you want to send and a completion queue to read it without having to do a system call. So it's in the right direction, but it too is not sufficient. It doesn't handle hardware queues, for example. And it also doesn't do RX. So the next thing I hit, should thank Eric for this, because I kind of got a little blinded by all these different variables that I'm going through. And I kept seeing SKB release data pop up in perf profiles. And I'm like, wow, this is weird. Like we just have way too much overhead going on with these SKBs, all the different fragments trying to represent the pages that are coming down. Eric made a comment in one of the NetDev discussions about huge pages. And I went, oh, yes, of course, right? Using huge pages, an SKB only has two mostly, and then occasionally when you're flipping from one huge page to the next, you'll get a third fragment per SKB. That makes a huge difference in your performance. But backing out a little bit, what this is generically saying is how the buffers from an application perspective are presented in that SKB as it makes its way down the stack or makes its way up the stack to the application. We've got to improve that. Got scripts, got hardware, congestion control algorithm, which is an easy sweep, just change a parameter. What this shows, cubic, DC TCP, you know, like all of them kind of behaved okay. BBR on the other hand, and I know there's BBR v2 is on GitHub, so it's in the works. I didn't want to deal with downloading out of tree software and compiling it and running those kind of tests. But BBR, which was really confusing, and we could not figure out why, it was flat. Pretty much flat and around, I think it was 150 gig. Hardware considerations. Speed is important. You're processing packets coming in at an insane rate. So certainly a faster CPU is going to help out. Avoiding CPU cycles is the best. One of the things we learned in these tests is that task placement had a huge impact on our performance. For example, our original CPUs were EPYC based, and 7502, I think, was the processor. They only had two CPUs. We disabled SMT, 2 cores per L3 cache. You could literally watch the performance of iPerf 3 tank as that process moved farther away from the K thread processing it. Right. So the key there is that if you're trying to run really fast, you need to think about task placement. In this case, what we found was the IRQ and the soft IRQ processing on, say, CPU 0, and the task pinned to CPU 1 was the best performance. Then we got these Ryzen boxes and the Zen 3, and the Zen 3 architecture was a lot better. That L3 cache spread out over more CPUs, and it was a little less sensitive. So the task pinning was more like, be somewhere in one of these 8 rather, as opposed to, you gotta be exactly on this one. Memory speed was another one. During a pandemic, you take what you can find, right? 2400 speed memory was not going to cut it. We had to go to 3200 to really push the EPYC servers. Luckily, all our Ryzen servers had 3200 speed. But that hardware failure we had at the end of June reinforced another lesson that we weren't necessarily thinking about as well as we should. And the change that the guy made to the hardware, when he had the Ryzen box open, he noticed a couple of the slots weren't populated. So he put in DIMMs in all the slots. And that was the difference. That was the only other change he made to the hardware that took us from a 680 up to 782 hardware speeds, right? So the key there is when it comes to AMD servers, at least, you got to populate all your memory slots to get your fastest speed. On the ring size, you can see this with Mellanox today, the ConnectX 5, ConnectX 6. 4096, you're dropping packets in the hardware. there. There's just too much time. The packet's coming in too fast compared to the time it takes for the software to wake up and start processing them, that you basically have to set that ring size to 8192. So that one worked best for us as well as FPGA. 16K didn't really make a difference at all. So I said this VCU 1525, it has two CMAX on it, right? So we can do 200 gig connections. Server has 16 cores, so hey, let's set up and let's run multiple streams. So this gets into the scaling out part of what we want to make sure is going to work, as well as that scaling up. So being able to run multiple applications at line rate, for example, or the way they're placed on the server. So anyway, of course, the theory worked out that you can run multiple things in isolation, of course. Kernel regressions. So we stuck on the 513 kernel for a reason. 515, and I'm fairly certain I know which patches it was, caused a regression. Got worse in 517. So our performance with 517 was 25% less than we could do with 513. And then we got a tiny bit of an improvement in 519. I think I know which patches did it in 517, but the key there is, it is that death by 1,000 paper cuts thing where somebody's coming in, putting in patches which are an optimization, which may not be an optimization for other use cases. So something we got to work through. Miscellaneous tidbits. You learn all kinds of things doing performance tests. One of those is Ubuntu loves this config option where if you go to the global allocator, it wants to zero out that page for you. Thing kills performance, CPU intensive. You got to disable that config option if you're trying to run high speeds. SMIs, if an SMI comes in on you, you got packet rates coming in the nanoseconds. One SMI, you're not processing your queues, you're done, right? You're not going to keep up. The other part of this was the absolute random things happening on a server. Someone would keep starting up LLDPD to do some validation on the networking configurations. One packet socket killed performance, and you spend all this time trying to figure out which one's got it, which one's doing it, who's doing it, right? So this really gets into this notion of generically, it's applications running high performance can be killed by something random. And so this notion of a packet socket cloning everything is an example of that. So in summary, we do think Linux TCP stack can be the basis for high scale computing, but there are some bottlenecks around the socket API that need to be addressed. We got to have a scheme where hardware places the packet payload data directly in the application buffers. Clearly by Kuba's recent blog post, Jonathan Lemon's ZCTab, lots of people are thinking about ways to do this. We got to have a better memory and buffer management scheme. This idea of dealing with pages, with ref counting, the DMA setups and stuff, all that overhead has to be amortized in a better way. LRO is absolutely essential. Software analyzing every packet that comes through is never going to work. You got to have a good, solid LRO scheme. And then the system calls for send message, receive message completions, that's got to go as well. And so again, the IOU ring notion of user kernel queues is a part of that solution, but it is still more to it. And then the last one is the simple representation of that application memory in the SKB as it traverses the networking stack. Okay. And then the isolation gives you that scale out and up capability. All right, so that was a whole list of things that we would like to see changed. We have a talk coming up in NetDev, which gets into one set of solutions on how to make this work with Linux. Thank you.
Hi, thanks for the fantastic sharing. I have basically two questions. First question is, I'm a bit confused, when you try to tackle this processors LP cache issue, right? Because in that generation AMD processors, usually have the DDIO similar features, right? And also their match system compared with similar generation.
I'm not having a hard time following you. Say the last sentence.
Okay. What I mean is that generation AMD lacks DDIO similar features, right? Compared with them. And also for the generation AMD, their MASH system, okay, MASH system for the memory, okay, also relatively weak compared with So I'm really confused why you try to use the AMD processor to tackle LP cache performance issues there. Right? I'm very interested to see the result when you run with isolate. I'm very interested. I don't know why you choose AMD. So that's the first question. The second one is
let's go to the first question.
Okay.
So I didn't pick the CPUs. So I joined the company only a few months in, but there was already a switch to use AMD EPIC. That was the preference. And it was a notion that I think a lot of the like the Googles and the Facebooks and such are all focusing on EPIC as a way to do their standardized deployment and their network. Right? So that was one of the reasons why. But we very quickly started tripping over a lot of these AMD issues. And some people in the company knew that the Zen 2 architecture was the culprit, so Zen 3 helped, and the Ryzen 9, which is Zen 3-based architecture, showed how AMD is moving in a better direction with the way they manage the caches as well as the memory. I was really sharing the CPU effects of that more from these are things that I tripped over, just to make people aware of it. Not trying to be critical of AMD or anything else. It's just these are just things that we hit and passing on.
Yeah, but I'm just curious, because TDI just there can solve the problem just like that.
Well, one thing we got to remember also is because we were not landing the data, TDIO wouldn't have affected it. Right? So we're not actually doing a TMA payloads. We simply have pages that we stick on the SKB to represent data. So TDIO kind of snooping wouldn't have done anything.
It's basically do anything because if all the traffic is cold, we inject all the traffic to the LP cache directly. Suddenly you have it. Okay. Second question is about the MPU size. The 7,000 looks like the magic number, 7,000. And notice in all your charts, once you hit the MPU size to 7,000, performance has a dramatic drop. So any reason for that?
I didn't analyze much of the higher MPUs. Because I think most people would agree. People doing data centers are not really jacking the MPU up into the 7,000, 8,000 range. It's going to be more like a 4,000 and under, or the 90, 9,100, 9,000 jumbo frames. The intervening data points there, it was just kind of some nice things. Things like the 6,800, the divs. 7,200, I think, would have moved to the smaller buffer sizes. Again, I was going to go after what exactly Linux is doing in the way that it manages the write queue, the socket queue, and how much data was constantly there and drained, and why suddenly there would not be able to push faster. Right? It just seemed like an odd blip to me. But when the server died, it affected everything. Right? I lost a month and a half of what I wanted to do for a data analysis.
Anyone else?
Thanks. Very cool talk. I see you doing a lot of testing on different technique size. So do you have sort of a recommended size overall after all the tests?
So the bulk of my testing, I kind of honed in on the 3,300, 3,400 MTU size, and that was in part because of Mellanox. I think my brain kind of got biased with some other testing that I was doing. If you watch Mellanox 5's the connect way the driver, unlike 5 driver handles connect 5 and 6. When you go above, I think it's 3560, it goes into non-linear, right? That's when you look at the way the page is allocated, the shared info, and the header part of that, and then the XDP reservations. If you try to do XDP on those servers, 3560, I think it is the limit you can go. So for that point, eventually I stopped going over 3,500. But 3,500 didn't perform as well as 3,400. At 33 and 34, it kind of went back and forth on which one was better. So when you look back at that chart, I don't know if this is still up here. You can see that really huge, really big ramp up at the beginning, which is where you're getting the majority of your benefit. And so it peaks out around 4,000, right? And then after that, we want to get higher MTU, only going to affect all of the boxes in the network, right? Because they have to allocate memory to land the packet, regardless of what size it is. A 64 byte packet comes in, you allocated 9,000 or 16K, you had to go power 2. You're wasting a lot of memory, right? So that's why I think the more realistic sizes are kind of in that 3 to 4,000. And I think Google's gone to 4,000 because of the RX0 computation.
Thank you. And then, any insight why DDR performs so badly and what's the surprise as a developer?
I didn't analyze DDR at all. We did dig through the code a little bit, had some conversations with some of the developers. I think really the focus would be on DDR-V2 to see how that performs. But you know, I downloaded that code at one point with 5.11 kernel, had to jump through some hoops to get it compiled and working, and then included those hoops again for the 5.13, 15, 17, 19 kernels. So I guess really kind of waiting for DDR-V2 to make its way into the kernel. And then, you know, we've got these boxes that can run the sweeps anytime something gets put in.
Happy to follow up offline, yeah.
Okay.
Usually there's been a couple of regression depending on the conversion.
Yes.
In 17, it says there is some suspect about you have some suspect about the possible symmetry. I didn't. So it would be interesting to hear it.
I think it'd be better for you to have a conversation with someone.
Okay.
Thank you very much, David.
Okay, now we have Martin Rao talking about BPF networking codes.
Yeah. Just waiting for him. Hello. Okay. Hi everyone. My name is Martin. I work in the kernel engineering team in Meta. Over years, we have added many features to the BPF and the lab dev in the kernel. And I also have been helping other teams in Meta to use these new features in our production. So over time, I got a lot of questions since the number of hooks in the networking stack has been growing for BPF. So I got a lot of questions on where a BPF program can be run in the networking stack and what can be done in each BPF program. So today I want to give an overview on all these, most of the networking hooks we have for BPF in the networking stack, and also share some user experience I got from our internal user in Meta. So, so here is a super high level Linux networking stack. So for the BPF hooks, we pretty much have, you can run a BPF program in most of the layers in this diagram. So let's start from the bottom at the driver. I think most people will be familiar with the HID-BPF because that is the most, one of the earlier hooks that BPF enabled in the networking stack. So you run at the driver, it handles the ingress packet. So the HID-BPF program is run before the socket buffer creation. So that's where most of the speed coming from, because the HID-BPF program is called before the socket buffer is created. So what can you do with the packet? So you can do the header manipulation. Usually you should be able to read and write the header from the by using the data and data end pointer. recently multi-buffer is added. So if your driver support that, you may need to use the load and store base helper to manipulate the header. You can also add and remove header from the packet by using the address head helper. So doing the encapsulation and decapsulation. So after you're done with the header, then you need to decide what you want to do with the packet. You can say return XDP pass to ask the kernel to pass it up to the stack for further processing. One of our use cases return XDP TX. So it will transmit the packet out to the same interface. We're using it for the level 4 load balancer. Other things you can do is you can redirect it to send it out to another interface or redirect to another CPU for further processing by using the XDP redirect helper together with the device map and the CPU map. So one question I got asked a lot by my internal teams, by the teams in Matter is, that's my favorite question all the days, is whether that socket is available in a particular layer. Because one of the motivation that user want to get a socket is they want to store something in the socket local storage that can be used later in the upper layer of the BPF program. So in XDP case is no, you don't have the socket because the routing is not done yet. So the socket is not looked up yet. But you can use the socket lookup helper to figure out the socket, right? One thing you can do is you can store data in the socket local storage. So for XDP, another useful thing you can do is you can reply a TCP SYNC packet with the cookie in it. So for example, your system is under sync front, is getting a lot of TCP sync. So instead of passing a TCP sync all the way up to the stack and then let the TCP handle it, which could be expensive, you can do it you can reply with a sync add with the cookie in the XDP program itself. So now we're done with the driver, we go up a level at TC. So we can also run the BPF program at the TC layer. So usually you probably want to run it at a TC ingress. So that's after the GRO. And for the egress, you can also run it at the TC egress host also. So for header handling is pretty similar to XDP, but one difference is the socket buffer has already been created. You can access the header through the data and pointer if your header is in the linear area of the socket buffer, which is usually the case. But in some case, somehow it's not in there, then you can use pull data to pull the data from the fragment to the linear area, or you can also use the loads and store bytes helper to work on to read and write the nonlinear part of the header. And you can also add and remove header by using the address room helper also. Since we have the socket buffer, so there are a few more things that's available. For example, the hardware timestamp, the protocol, and many other things you can find from the normal kernel socket buffer. So for the hardware timestamp, I know Jasper has XDP hints packet set post out there. So hopefully the hardware timestamp will also be available in the XDP program soon. So after you're done with the header, reading, writing, what can you do with the socket buffer is also quite similar in the XDP. You can return OK to say pass it up to the stack for further processing, or you can shut it down to drop it, or you can redirect it to another interface that we use it in Matter. Is we use BTP redirect helper to redirect the forward packet between the physical EIF and the virtual EIF of the container. So we forward packet at the TC layer instead of passing it up to the IP layer and routing layer to do the forwarding. So that is much faster. For the egress, BPF hook at TC, one thing we do also is we set the delivery time and the timestamp. So together with the FQ disk, so we can do that, do the bandwidth shaping or limitation in a very fast and flexible way. So my favorite question again, is the SK available in the egress? No, because the routing is not done. But you can call the SK lookup helper again to look up the SK. That is similar to the XTP, but one extra thing you can do at TC is because the SKP has been created, you can call the SK assign helper to assign this SK that you just look up to the SKP. So you can think of it as an even earlier demarcs. For egress, you should have the SK pointer because the packet is created locally for the same message, right? So we are done with the TC layer, so we go up now. So when we go up, it'll be useful to break it down from the left diagram to the right diagram. So the right diagram has more details on each individual BPF hooks we have above the IP layer. So from the bottom is routing that's done by the kernel. So when the kernel decided a packet, after finished routing, the kernel decided the packet should be handled locally. So we routed locally. The kernel need to find out which socket should handle this SKB, right? So the next step the kernel need to do is to look up the socket. So there are a few BPF programs that we can change which socket to pick from the system. So the first one is SK lookup BPF program. It is a per network namespace program. So you attach this program to a network namespace. So what you can do is for a TCP sync packet, you can choose which TCP listening socket to use. For the UDP packet, you can pretty much choose which UDP packet to use as long as the UDP socket. You can choose any UDP socket to use as long as that socket is ready to receive packet. So as long as so there's the SKP is available in this program, but it's read only. You cannot change header at this point. So usually what you want to do in this SK lookup program is you want to pick a socket that's not bounded to the IP and port that this SKP is sending to. It can be based on your level namespace policy or whatever you can think of, I think. But usually what people do is you have a pool of sockets stored saved in a sock map or sock hash. It's a BPF map, and then you pick one from them, and then decide to use that socket to handle this socket buffer. So after the SK lookup, another BPF program can pick another socket is SK reuse port program. For this program, it is attached to a particular socket. So you can attach it to a TCP listening socket. So for a reuse port socket in the kernel, it's like you have a group of reuse port socket. It is bounded to the same IP and port. So the user setup is like you have, for example, you have 10 worker thread, user level worker thread, and then each of them will have its own listening socket. But all of these 10 listening sockets will be bounded to the same IP and port to serve the traffic. So by default, the kernel will pick one from out of these 10 by using the socket buffer hash. But the SK reuse port program can pick one differently. For example, you can pick one based on the numero. What we use it for a lot is that we pick one, we avoid picking the listening socket that we know the process is going away. For example, during the process we start, the user need to, for example, the user need to upgrade the binary program in the user space. The program need to restart. Then our program will avoid picking the listening socket that we know the process is dying or going away. Instead, we will steer the TCP sync packet to the listening socket belong to the new process. Another thing we could do for TCP is imagine you have the old process dying and the new process is running, and then there's some newly established connection is still in the listening socket, old process listening socket accept queue to be accepted. So we can move them from the old listen socket accept queue to the new listen socket accept queue. So when the old process will eventually go away, we don't necessarily abort those TCP connection and by sending TCP to send things. So that improves the user experience. Another thing we also look at for quick, we also look at the connection ID and then pick the UDP socket accordingly. So SKP is available, you can use it, but also it's read only. You cannot change it at this point. So now the socket or the BPF program has picked the socket. So from the socket, we know the C group, right? So now, since we know the C group, we can run the BPF C group program. So one of them is the C group ingress and egress. So those programs can handle IPv6 and v4 socket buffer. And the socket buffer is also read-only. But since we picked the SK, so the SK is available now. For ingress, you can reject the packet based on different container policy. For egress, you can do a similar thing as the TC. We can also set the delivery time in the socket buffer timestamp and use it together with the FQ QDIS to limit the bandwidth per C group policy. So for C group egress, one extra thing you can do is you can return transmit drop or transmit CN, so that this signal can send signal back to the TCP stack to do the TCP enter C-ring reduction function. So we'll take a break from the C group program. One thing I want to talk about is a BPF program called BPF TCCC, which is backed by this drop ops BPF program. That's TCP only because it is essentially a TCP congestion control algorithm, which can be fully implemented in BPF. So we have example to fully implement the qubit and DC TCP in BPF in the kernel source tree self-test directory. So the main motivation for writing the TCP congestion control in BPF is to enable the networking experts to test the congestion control ideas easier and faster in production without worrying about panicking the kernel. So we already have at least 2 TCP congestion control running in the production. So one of them is dedicated for background bulk traffic use, and we save money by not having to over provision the backbone bandwidth. So another one is the guys are also actively testing different ideas to optimize the DC TCP in our environment. So a lot of experiment is ongoing. I can tell that a few versions of them running in the production. simultaneously. And guys are also testing a lot of one-way delay idea and use it as a congestion signal to the congestion control algorithm that they're writing. So before I switch back to the C group BPF program, one thing I want to mention is one extra thing I want to mention is about the BPF TCP iteration program. So now we can roll out the congestion control much faster. So maybe we want version 1 this week, version 2 next week, and then version 3 by the end of next week, something like that, right? So we have a lot of different versions running in the production. So one problem we have is for the long-lived TCP connection, and they're holding on to the old TCP for too long. So one thing we used to do is to force restarting those services to kill all the TCP connection, so that they will pick up the new congestion control algorithm. So now we're doing it a little differently is we have a BPF TCP iteration program. So what it does is it iterate all the TCP connection in the machine and then call the BPF TCP iter program. So that program can do many things. One thing people used to do is like printing out some statistic or collect some statistic in the map and things like that. But one thing we do now is we will look at this connection when we're iterating each connection. We look at each individual connection and see whether they're using some congestion control which is too old. If it is way too old, then we will call Seccomp TCP congestion to force upgrade them to some newer congestion control algorithm. So next, we'll go back to the C group BPF program. So next one, I want to talk about SOC-ops and with the S. So we usually use it together with the BPF TCP CC to change the TCP connection parameter. So it is actually one hook in the TCP. It's a one hook BPF C group program, but the kernel will call this BPF program at different time when the TCP connection is transiting to different TCP state. For example, when it is transiting to the listening state, it will call the SOC-ops BPF program with the listen callback. When it transits to the established state, it will call the SOC-ops BPF program with the established callback. So one thing you could do is during this state transition, you can change the TCP parameter differently. So for example, one thing we do is, for example, when the connection transits to the established state, we could look at the peer IP address and then do things differently. For example, if we know that peer IP address is from a data center far away, then we may decide to use a different BPF TCP congestion control algorithm. Another callback you will get is a timeout init. So how we use it is we'll set a different retransmit timeout. In ISO, we transmit timeout for the TCP send and TCP SYNAC. One last thing we could do here is add different TCP header options. For example, if we know that both peer is within our data center, so in this case, we have a lot of flexibility to add our own TCP header options there. For example, we add the server ID in the TCP send packet. The idea is pretty similar to the connection ID in Quick. Another thing you could do is to set you can tell the other side what maximum delay add you are doing locally. Then the other side can use a lower RTO. So the last set of the BPF C group program is sitting at a syscall code path. For example, connect, send message, get, sort, PNN. So usually what we do is try to change the local and remote address when the user space is doing connect or doing bond. Another thing in the syscall code path is the set and get sort out. So one thing we do a lot is when the user space call a set sort out, then we will do something more underneath the user space. For example, when the user space calls set sort out IPv6 traffic class to specify, hey, I'm sending some background bulk traffic, then underneath the BPF program will know that, and then it will switch the congestion control algorithm to use the background bulk traffic congestion control V1, V2, V3, V4 as we roll out different versions. So when we roll a new version, congestion control version, we don't have to change the user space. So everything will be transparent to the user. Recently, we have BPF LSM secret hooks added by Stans. So that will enable more syscall code path to run the BPF program. I think he will have a presentation on this, so you can learn more about what you can do there also. So I think I will jump to the last common question I got internally from other teams in Matter, and that's the hot question I got in the last 2 months continuously. It's about C group storage. So the question is, the confusion or question I got a lot is we have a TC program, and in the TC program, there's a SKB. From the SKB, we have the SK if it is egress. And from the SK, we know the C group. So can we get the C group storage? And the answer is no, we cannot do that because the TC is not a C group program. But then it's quite confusing, right? Because the socket, task, and ILOC storage doesn't have this limit by different BPF program types. So pretty much all BPF program types can use the socket local storage. Even the tracing can use it. So another question I got around the C group storage is a BPF program can create multiple socket storage map. But that cannot be done for the C group BPF program. The C group BPF program can only use one C group storage map. So I don't have a good answer for my teams because that turn into some low-level implementation details about C group storage. But Yonghong and I have a quick chat on that. I think it will be useful to have a very flexible C group storage as the socket and task storage. So it is one thing in our to-do list. So another fun things I got complained a lot is about the socket helper is not available in some of the hooks. For example, the sort ops, it is a C group program, and then the user want to learn the C group ID by calling SK C group ID, but it's not available. Another example is get socket cookie. So for the TC program, it can get socket cookie from the socket buffer, and then essentially it's getting this socket cookie from the socket buffer SK. But if the TC program do a SK lookup TCP, get a socket pointer, then you cannot get the socket cookie from this SK pointer. So going forward, we should allow all these SK helper to all the hooks if it is safe to do that to minimize user surprise. But this one I also get some complaint from time to time. It is a socket helper, and should the user pass the context pointer, or the user passes socket pointer. So for example, for the set of helper, the function selector is void asterisk BPF socket. If we look at the comment, is if your program type is this and that, then you should pass the context pointer. Everything else you should pass the socket pointer. And the same thing happened to the get socket cookie. And most of the time, for all this program type, the context can also get to the socket pointer. So the user first reaction is try the socket pointer first, and then get rejected by verifier, and then they will try the context pointer. So going forward, probably we should stay with the socket pointer for helper, or even for we are moving to K-fun, then the K-fun naturally should take the socket pointer instead of taking the BPF running context. So for the existing helper, maybe we can improve the verifier to allow both, so that the user will have less surprises on this. So that's all I have. Any questions?
So you mentioned many hooks, and how can we expect more? Sure.
Sorry, can you repeat the question?
Can we expect more hooks in the future? Even more hooks?
Do you have example? We cannot edit it. If we cannot say edit anywhere, right? If you have some concrete use case here, maybe. I don't know. Do you have some hooks you have in mind? You want to add?
No, but I think we are thinking about having some analytic system here, and in some cases, it's hard to answer if it will be possible using those hooks. So is it fair to say that if we come up with a use case that is not supported, then there is hope to add more hooks?
Yeah, but for the hooks, the way that you add hooks, we'll be going back to Alex's presentation earlier this morning. Right? How you add it is also we'll be going to the modern BPF column that Alex mentioned in the morning.
I have a question about the GR or the GSO layer, because it seems like in the driver layer you have executed, and then above that you have the TC. What about that layer, the GR or the GSO? Do you anticipate any codes being added to that?
No, I don't know, because what GRO doing, for example, what GRO doing is like merge the socket buffer, right? And then if they have the same header, then you merge it. If you can think of a use case, if we can think of a use case that we want to combine socket buffer differently other than the header, maybe, I don't know. Do you have a use case?
No,
Anyone else?
Another question, but maybe more of a comment. I think we were too conservative with exporting which helpers, which hooks can be used. I recently did this like set value things. I think we should do something like that for everything. Basically, because usually what I struggle with, I need to use some helper and some hook, and it's just not available. And then it's just a matter of going and adding it to this speech case, right? And it's, every time I use it, I hit the wall. But we should basically, I think we should go back and reason which helpers are available to which hooks and extend those bits and make them more.
Yeah, I agree. For example, let's go back to socket, right? We should go back to exact all the socket BPF helper and then just make it available whenever it is safe.
I don't know, maybe we could think of it safe, but
definitely good.
Anyone else? All right, thank you very much. Thanks. With that, I think it's lunchtime.
Like it's really not all.
Check. Yeah, I think we should start, and if whoever wanted to join, it's probably the time. So, KP and his talk about BPF signing and IMA.
Cool. So the talk is about BPF signatures and how is it going to be integrated with IMA. I want this talk to be interactive. Now we are relatively a small room that is fairly spread out. There are some discussions that we need to have. Plumbers was generally more discussion oriented, so I hope we can keep it this way. So why do we want to sign BPF programs? The main thing we want to have or establish is that the BPF program comes from a trusted source. So imagine you have this BPF program, you have your tool chain, you're building it on a trusted server, or you could be a distro, you could be somebody who deploys BPF programs in a data center or something. And then you have a private key and you only have it on your build server. You sign the BPF program with your private key, and then this could be verified in the kernel with a verification key or a signing, with a verification key. So yes, build time security for BPF programs. So the main requirements we have is, first thing, we go with the principle for BPF, that is, it has to be flexible. Whatever approach we build, we want to keep, anybody should be able to implement their signing, their own fancy crypto, whatever they want to roll out, they can use that, as long as they provide the right helpers in BPF to verify these signatures, or in the kernel somewhere else. The other requirement we have is the stable BPF instruction buffer. Now, with all the goodness that Andri's core has added to BPF, what it does is that there is no BPF object file that the kernel knows about. It's just an object, it's just a buffer of instructions. And these buffer of instructions, as you compile them on the build server and you sign with your private key, this would change on the system that you load the BPF program on due to runtime relocations. So you really need a stable BPF instruction buffer, and we'll see how we can solve that. We have partially solved that even now. This is a more important discussion for the BPF room. How many of you folks know about IMA? Okay, so I actually tried to search, when I was reading for IMA about the first time, I tried to search about Wikipedia articles or whatever, what is IMA all about? And essentially it boils down to that trusted source problem for executables. If you're running executable code on your system, it needs to come from a trusted source, and it's a policy framework. It's a classic pre-BPF approach where you have a file that you say, all executables on this source need to be signed with this key, and this is the verification key for that. And yes, so that is essentially what IMA is about. There is another complementary system called EVM, which is more about the metadata. It wants to ensure that the metadata also comes from this. And of course, IMA has its own hashing format. It has its own, it stores the hash in an extended attribute on the file. And this is, again, it goes a bit against the whole flexibility argument. So what are we going to discuss here, right? We want to know, how is the policy for the signature verification specified? Is it going to be a protobuf? Some people like to use protobufs, right? Is it going to be the IMA policy format, right? And the other question itself is, how is this policy going to be verified? How is the verification going to be implemented? The first bone of contention is the policy specification only IMA? Of course, we know the answer to this in the BPF room. The answer is no, right? We want the policy, we want the users to be able to build the policy in the form they're most comfortable with, right? This could be just a raw BPF map that specifies the policy, or some fancy language that they can then convert and communicate the policy to the kernel. Only custom policy formats, no IMA. This is also not a great solution, because some distros are already bought into IMA, and they would like to use it for BPF as well. So you would want to extend the IMA policy format for eBPF programs as well. With the same goal, executable code should come from trusted build servers. The first proposal we have is you support the IMA policy format and you support custom policy formats with BPF. Easy to check. Now, verification logic. We could also implement the verification logic in the only integrity verification framework that is there in the kernel, right? And the answer is IMA does come with a lot of overheads if it is enabled for everything. We don't want to do it just in the IMA for a subsystem. It is not a flexible approach. This is something we've considered before. Only implement the IMA logic, the BPF program signature verification logic in BPF itself. Now, the way we could do this is BPF has helpers for all the IMA stuff, right? IMA installs distros who you want to use IMA. They would maintain this, or they would write a BPF program in the BPF LSM that would use IMA helpers to parse the IMA signature format and keep the logic in BPF. Now, we had discussions about it at the Linux Security Summit, and this is something that is not very appealing to the IMA developers. They're like, we don't want to expose all the IMA API to BPF, and we don't want to maintain this BPF program, or distros may not want to maintain this eBPF program that verifies the policy for IMA signatures. So, yeah, so both IMA and BPF programs should be able to implement a signature verification. And this is the core point where the signature verifications happen. It's in the BPF prog alloc LSM hook. It's before any of the verifier changes any instructions in the kernel, so you can verify the signature there. And you can imagine BPF LSM calls out into the BPF program, and the integrity subsystem provides its own hook or directly hardcodes the logic in the security BPF prog alloc. The issue is that IMA is not an LSM. IMA is part of the LSM command line. It is part of the whole security system. But there was discussions in the initial days of IMA that it was integrity is separate from security. So then IMA exists as this weird thing that after all the LSM hook iteration happens, there is a separate call out into IMA that verifies and appraises signatures there. But I think I had a chat with Alexei as well. It sort of is fine. If IMA doesn't want to be an LSM, it is still okay as long as it doesn't override other LSMs with their negative decisions, which it doesn't in this case. So yes, we go into the implementation details a bit. Like the signature it's stored in a buffer. Like this is a void star pointer that is part of the attributes in the BPF syscall. This is an anonymous buffer. You can do whatever you want. IMA can prefix IMA SHA-256 and the hash after that. We can provide a simple signature reference implementation with BPF. That's basically what it looks like. This is the thing that ends up getting signed, the instructions, and like the instruction count is of course the size. And then you get a signature back and you have a signature size there. Yeah, that was the core. This is what IMA integration will look like. And I think what the IMA folks want it to look like for now. They want this separate call out after the LSM hook iteration happens. They want this like IMA BPF prog alloc hook into IMA. So if BPF chooses to implement, BPF LSM chooses to implement an integrity and says, I don't agree with this, right? This is not verified per my policy, then they can still say no. And IMA gets the last say, effectively. So it's a weird architecture, but it still works. I don't want to dig into the history of it. If we are fine with this, then I can convey it to IMA folks who haven't showed up here yet. I think this is something we've discussed in the office hours as well. Light skeletons is the answer to the stable instruction buffer and the core stuff. Light skeletons, does light skeletons support core yet? Not for me at least. Okay. So light skeleton, yes. So light skeletons is this version of BPF skeletons which generates what we call a loader program. A loader program is a trace of all the syscall operations that would be done when you load a BPF program. when you load a BPF program, it's not just the raw instruction buffer or BPF prog load that happens. There are multiple syscalls that happen along with that. And so, for example, you are interacting with maps, you're setting up other objects, right? And the loader program is a trace of all of that. And what we end up signing instead of the actual instruction buffer, which is pointless without all of these operations that go along with that, is you sign the loader program and the instruction buffer. And the relocations, since this supports relocations as well, like the instruction buffer doesn't change here. So you can sign this and the kernel can verify this as the buffer remains stable. Does that answer your question about light skeletons? I added some, and I'm going to send these an RFC on the after the Plumbers conference. But there is a basic BPF tool support. This is like PKCS number 7. I always get those two wrong, which is like kernel module. So BPF tool has this. And you can imagine BPF tool can be extended to provide IMA signatures, or IMA can write their own user space tooling. They can integrate it with EVM-CTL. But this is one signature format that I'm proposing as an initial reference, is that it takes a private key path and it takes a X509 cert, and then you provided the instruction buffer and it generates the signature that embeds in the light skeleton. And that's what the command line roughly looks like. So you do a BPF probe load. You can, if you want to be, you're just trying out things, you can just, or you think that BPF tool is trusted, then you can, then you can, and you have the private key on the server that you need the signatures for. You can provide the private key there and load the program directly from there. You could, but typically how it will look like is on the build server is that you will generate a skeleton file and some user space object will load that. And then the signature gets embedded in that skeleton file. So if you look at the BPF source code, this is like, or a BPF self-test, it is like .lskel.h, right? And then it has like a bunch of the overall instruction blobs, and it has this signature embedded into it. I can show it to you, a bit of it at least, from the kernel source code after this. Yeah, so I'm going to show you a bit how the BPF program and the skeleton stuff looks like here. Oops. Yeah, so this is essentially the BPF verifier, or we call it the gatekeeper program. That is the implementing the signature stuff. And this is the, oops, yeah, this is the one. So as you can see, it is attaching to the BPF prog alloc security LSM hook, right? This is just for the test. We only want to limit the impact of running the test on the PID of the test. We do that for a lot of these tests. I added this is kernel attribute into the aux field of the BPF prog, which is the thing that is passed to this LSM hook, because as you can imagine, this loader program is going to run a bunch of other syscalls, and it's going to load the actual program as well. But this program loading is happening from a helper within the kernel. So you don't really need to sign that. You've already signed the overall loader program. So if the syscall is originating from the kernel or from the BPF program, i.e. the loader program, you can skip that check there. This is something I was discussing on the mailing list yesterday, is that currently the dynamic pointer support, you really have to read the signature is in this struct. The API that Roberto has proposed, the verification API, takes something we've developed in BPF called dynamic pointers. You can create dynamic pointers from memory that is allocated to a map, from memory that is allocated to like a ring buffer. But when I tried to create dynamic pointers from memory that is allocated from this like data val -data, which is a void star pointer, that didn't work. I think Kumar was mentioning that this is generally not going to be possible, and you'll have to annotate it somehow that this is some place where you can create dynamic pointers from. I think his second suggestion on the mailing list is actually quite valuable. It makes more sense. You can create a dynamic pointer in the auxiliary structure itself so that it can be used here. But then this is exposing a bit of like somebody in IMA who wants to use that will now be exposed to this dynamic pointer stuff, which I think is okay, because sometimes when you want to use IMA and BPF, we have to deal with their internals as well. So yeah, and then we look up this keyring. Like I signed these, I updated the make file that if we have config mod sig enabled, it will, all the BPF tools light skeleton commands will actually generate a signature using the signing key and the X509 cert that is created for the modules. And then we opportunistically run the self-test if config module signature is enabled there. And this sort of works. I would like to pause now and ask for questions, because signing would be should be something that distro people, if they are there in this room, would have some say about.
I just wanted to say, and without getting into the history, but the reason why IMA is not an LSM is more mechanical than it is conceptual.
Okay.
And there's a lot of work that's going on where those mechanical reasons are no longer going to exist. There might be some work to get that done, but I think conceptually it would be much better if IMA would be an LSM, and I would support that. I know you're going to get pushback from the IMA developers, but if this is something, if it makes your life easier, I think it's worth having this discussion again with Mimi. And if you want, bring me into it and we can talk about that.
That'll be, I think we should discuss it at the LSS as well. This is perfect. Hi, Paul.
Hi, one question. So you are loading eBPF program to do the verification of the other programs, right?
Yeah.
And what do you do to verify the initial program that?
So either you can have it built in the kernel itself, like
Okay.
this is something that we discussed in LSFM and BPF, is that it can live within the TCB, right? Or you can have it loaded by some process that you already trust. For example, systemd or whatever. And then you can prevent all BPF loads before that. Or you don't care about security before that because you know nothing can happen in the system before this process really starts. So either some trusted process in the boot sequence or embedded in the kernel, which is already provided by like the BPF preload stuff that is there in the kernel.
Okay, thank you.
Hi, thanks. It's probably quite minor, but BPF tool can use a PKCS11 token for signing.
Sorry, can you repeat that?
Can BPF tool use a PKCS11 token for signing?
Of course. I mean, this is just what I
just
know.
OpenSSL under the hood? Or
I think it internally does use that. I saw this is because Roberto's patches implement PKCS 7. I use PKCS 7, but yeah, we are all up to discussions on these. What signature is the right?
Oh no, it's the same type of signature. It's just it means using a physical token for signing instead of signing by software. But if you're just using GNU-TLS or OpenSSL or something like this, so it should just work, I assume.
Yeah, I mean, like it's the whole thing that the kernel modules uses, but without the format string before that. Like all that header that the kernel module adds, I've not added any of that.
Should be fine. Otherwise, I can fix it.
I guess you also need the function in the kernel to do the verification, because with PKCS 7 you use the kernel module infrastructure, and for PKCS 11, I don't know if you have something there.
So what I saw in the kernel module code is that there is a sign file.c that does that generates a signature for kernel modules, and that already does a PKCS 11 signature.
So that sign file just uses OpenSSL, and you can just pass a PKCS 11 token instead of a key. So even if BPF tool doesn't have the plumbing for that, it's probably trivial to add because the infrastructure is in either OpenSSL or GNU-TLS or whatever you're using to do the actual signing, not re-implementing the crypto there. And all those libraries should be capable of using a PKCS 11 token.
So one thing I don't like about my implementation is that it is picking a lot of code from the sign file.c. This is like old OpenSSL, like one something code. And we have, when I initially ran the build for this, I got a lot of warnings for OpenSSL 3. Is there, I think, can we share some of this code? Okay, cool. That's good. Are you the maintainer for this? Okay, okay. I mean, I thought we will have some agreement on the next Plumbers here already.
Nice.
Hey KP, could you walk through the BPF trace use case, like the trusted code generator that kind of generates BPF instructions on the fly, loads it into the kernel? How would that work in this world? Because I know that's been like a contentious.
So I think then what you would do is, since the policy is, of course, IMA would have its own policy, right? IMA could allow list some of these things if it has an exception mechanism for this stuff, right? But what you can think of is that, so the BPF program is something that you own, right? You could tag these with an extended attribute of some sort. Like, again, that discussion I wanted to have the exciter discussion after the signature discussion of some. Then you can imagine that when you load the file, you can start tagging things with the extended attr, and in the process, like I'm opening a BPF object file of some sort, and then in the program you can have hashes of the file that says only these are the executables that are allowed to load, like unsigned BPF programs, and you will have that information in your gatekeeper program that we're loading here. So BPF tool will have an exciter set, like I can load unsigned programs, and you can convert it to a task blob, and this will be passed to the BPF LSM hook. Ooh, we can have interactive sessions in this, Plumbers.
How tightly coupled is signing to skeletons, which seem to be a libbpf concept? The reason I ask is there are other libraries out there like Seccomp, which is not a libbpf-based library, and I maintain a Rust library, and it would be nice for signing to work for Rust too.
Currently, it is coupled to the skeleton stuff, but there is no reason for it to be coupled there. Like if we can come up with a stable signature blob that we can in these libraries as well, we should be able to sign it. It's just that for initial reference implementation, for what made sense to me to demonstrate is that create a skeleton with a BPF tool, right? Sign that skeleton, light skeleton or with a loader program, sign that, and then verify it in the kernel. But since the whole system is flexible, you have these attributes, you can implement signing as long as the instruction buffer you generate is stable.
Okay, so, and are you signing the set of instructions that are generated after relocations? Is that the reason why you want to do it with skeletons? Yes. Okay, cool.
So this is something I wanted to ask Andre actually, like where does the core relocation happen for loader programs? I don't know, how does it magically work?
I'll redirect it to Alexei.
Andre is best at delegation, as you can see.
Brilliant.
Yes, it does happen in the kernel. But what was the question?
So, like, how does loader program or like light skeletons handle core relocations? The answer is that it happens in the kernel after the signature is verified. Okay.
Well, kind of both. Well, it happens. The main thing to realize that all of the relocations, whether the map relocations, BTF ID, kfunc IDs, and there are like 10 different things there. They all happen after signature was verified by the kernel. So it happens in the kernel, and some part of it, a part of the eBPF that compiled with the kernel, and some part of it are instructions generated by the BPF tool as part of the loader program.
Okay.
Could you repeat again?
They are signed, those instructions?
The whole thing is signed, yes. So like the whole loader program, it contains like everything. So it's actually two pieces, the loader program as instructions and data for the loader program. Both need to be signed.
Surprised no one pointed out that light skeleton is not skeleton, and conceptually it's actually not tied to eBPF. Like right now it requires some system-wide headers, but light skeleton is designed to be not tied to eBPF. So, correct? Any other questions?
Cool.
All right, thank you, KP.
Who's next up?
Okay, next one, Jing Hao, if I say it correctly. And
Thanks.
BPF. Oh,
Am I
it's.
supposed to take the presenter here? Oh, nice.
Yes.
What's the problem?
I think you are a presenter, right? You should be able to.
Yeah, I think I already got access.
Perfect.
All right, revisiting eBPF Seccomp filters.
All right, so hello everybody, and I'm Jing Hao from UIUC. Today I'm going to revisit the eBPF Seccomp filters, and as some of you may know, this has been a topic that is discussed in the kernel mailing list for several times, and I believe it would be nice to have a discussion here at LPC. So Seccomp is the syscall interpositioning mechanism in Linux. It restricts the set of syscalls for an application, and therefore it enhances the syscall security for the application. Seccomp has two modes. It has a restricted mode, where it only allows read, write, exit, and seek return, and it kills the processes if other syscalls are used by it. But apparently, the restricted mode is too strict and not really flexible. And therefore, later, for the sake of flexibility, Seccomp added a filter mode, which allows to use custom policies implemented in the classic BPF language. This means user can specify a custom set of allowed or disallowed syscalls for the application, and also together with the actions to be taken when those syscalls are encountered. Seccomp filter mode uses CBPF language. CBPF is a simple language. It has a small risk-like instruction set. It only allows forward jumps, which means you can ensure that your program is always going to terminate. And then there is an instruction length limit also on the CBPF filters. All of these combined together makes CBPF easy to verify against safety properties, which is really nice for Seccomp because apparently Seccomp is a security-sensitive context. So this Seccomp CBPF filter mode currently it's widely used in practice. One of the largest group of users are those virtualization technologies and containers. We have, for example, Docker and Kubernetes. They all support using Seccomp to restrict application behavior. And then as a syscall interposition mechanism, it is also widely used in sandboxes, as in systemd and Android. So there are various other applications that are using Seccomp just for the sake of syscall security, like OpenSSH and web browsers like Firefox and Tor. But despite the popularity of the CBPF filter mode, there are some fundamental limitations of CBPF. So first, CBPF it's stateless, meaning it will in Seccomp it can only support static allow or deny lists. And then the fact that there is a set limit in Seccomp, when you have a complex policy that cannot fit into one CBPF filter, then you have to break your filter into multiple small filters, and this basically makes the control flow implementation harder, and also chaining all the filters together incurs additional performance overhead. CBPF has the simple instruction set, and this means it will not be able to use the advanced utilities like eBPF maps. And lastly, there is a programmability issue. CBPF does not have the two-chain support like eBPF. And so, for example, to write a filter in CBPF, you have to be writing CBPF instructions by hand, which is not really, not too different from writing assembly by hand. And then to summarize, CBPF, it cannot express complex Syscall policies, for example, state-based filtering. So because of the limitation, the idea of porting eBPF to Seccomp has been discussed in the Linux kernel mailing list. And here, today I'm going to revisit the eBPF Seccomp filters to basically see how eBPF as the Seccomp filter language can improve programmability and extensibility of Syscall security in Linux. So comparing to CBPF, eBPF provides a new level of programmability. It has a richer instruction set and more flexible control flow. And we now have eBPF map structures, which are efficient storage primitives. We have eBPF helper functions, which allows a richer interaction for the eBPF program with the kernel. And then we have better two-chain support for eBPF. eBPF is supported as a backend, as we all know, in LLVM. And this essentially means we can just write C code and then using clown to compile it to eBPF. So what does this all mean for Seccomp, though? With a new instruction set, we are now able to express more advanced checking logics. And then since we have the map storage, we can now store states for the filters across filter runs. And by using those kernel helper functions, the Seccomp filters can now have access to more kernel and process context for Syscall filtering. And then, as I mentioned, the mature two-chains makes implementing those filters easier. So as I mentioned, there have been several previous efforts to, and patches to port eBPF to Seccomp. Here, we listed two of them. In the first patch, it has a Seccomp program tab specifically for eBPF. And then on the Seccomp side, it adds the support so that Seccomp will allow using eBPF as its filter. However, in this patch, no map support is implemented, and there's not really a systematic security model. As for helpers, it only supports 4 helpers. And the second patch, which came out at roughly the same time, it's largely incomplete. It only has a new eBPF filter mode in Seccomp that loads and allocates the filter. So given that there are a lot of discussions in the kernel mailing list, we actually took a look at the responses from the community, and we categorized the responses into 2 main opinions about this issue. And the first, it concerns that there is not really a use cases for eBPF support in Seccomp. So what is the reason for adding eBPF support? Seccomp shouldn't need it, and it only makes code more complex. I'd rather stick with CBPF until we have an overwhelming good reason to use eBPF as a native Seccomp filter language. And the second opinion concerns with the security problem. So this is the blocker as far as I'm concerned. There is no story for unprivileged eBPF. And even if there is a storage here, I found the rate of security-related flaws in eBPF to be way too high for a sandboxing primitive to depend on. I just cannot bring myself to accept that level of risk for Seccomp. So in my talk, I will be addressing both of the concerns here. So let's first take a look at the use cases. So in fact, we found a lot of use cases that can only be done in Seccomp eBPF. Those include Syscall count limiting, enhanced temperate Syscall specialization, and Syscall flow integrity protection, checking Syscall sequence to implement, intrusion detection system, and also potentially accelerating security checks. Those use cases have the, what those have in common is that they either require the state support from eBPF or the mature two-chain support. And there are many other use cases that I will not have time to go over here. And in this talk, I will be focusing on the first 3 use cases. All right. So syscall count limiting. This is actually a real-world use case that is brought up by Andrea Agajeli, the author of Seccomp, who is now working at Red Hat. So basically, when the container runtime tries to start the application, it will first perform a series of setup steps before it finally exec into the target application. So we can take a look at the example runC code. So here, we're setting up our Seccomp filters. And then we fix up the namespaces and also sets the correct privilege. So usually this means dropping privileges for the target application. And finally, we exec into the target application. So the important thing to note here is that without the no new privileges attribute being set on the container runtime, Seccomp is a privileged operation, and then this basically means this Seccomp step, which installs the Seccomp filter, needs to be done before we drop the privileges in later in other setup steps. So in the later setups, namely those setups that dealt with namespaces and privileges, at this point the Seccomp filter has already went into effect, and then the syscalls for those setup steps must be allowed in the Seccomp filter. This is because once the syscall is blocked, it cannot be unblocked. So if we just block it in Seccomp in the previous step, then the container runtime is going to break because it will not be able to set up the correct privilege and namespace. So this means that CBPF filters will not be able to block those setup syscalls during application run. And then if the application is not supposed to be using those syscalls, I mean, under normal circumstances, then those syscalls becomes the additional attack surface. And the solution is to actually use eBPF to implement a state-based policy. Here, I'm showing an example of how to use eBPF to implement a filter that only allows the active syscall once for the container runtime. What we do is that we use an eBPF map to store states. So here, what we store is basically whether accept has been called. And then if accept has not been called, then we know that the container runtime is calling it to basically start the target application. And therefore, we just allow the syscall and then mark accept as called. Otherwise, if we're seeing the accept again, then we know that, okay, the container runtime has already started the target application. And that means the accept is coming from the actual application, and the application it's not supposed to be using it. And therefore, we just reject the syscall. And in this way, the additional attack surface is effectively eliminated. We also identified other advanced syscall policies that benefits from eBPF support. An example is temporal syscall specialization. The basic idea is that application can be divided into multiple phases where each phase exhibit different syscall behavior. And we just restrict different syscalls at different phases of an application. So take the web servers as an example, because those applications can usually be divided into just 2 phases, an initialization phase and the serving phase. And in the initialization phase, it only calls the init syscalls, and in the serving phase, it only calls the serving syscalls. Using CBPF will now be able to enforce the policy processly because the CBPF implementation installs a additional filter at the phase changing point. So basically, it's here, and then block the init set of syscalls, so that the serving phase is left with only the serving syscalls. However, at the init phase, the serving syscalls has to be allowed because, as I mentioned, once the syscall is blocked, you will not be able to unblock it. So in this way, the serving syscall in the initialization phase becomes yet another additional attack surface. And then, this is a simple example with just two phases. What if we have an application that has, potentially a lot of phases? Then our syscall that's going to be used by later phases of the application has to be a lot in the earlier phases, which means your attack surface now grows much larger. So what we can do is that we can use an eBPF map to track the application phases, so that we just use different policies for different phases of the application, and then each phase will just get exactly the set of syscall it should be calling. And the last use case I want to discuss here is called syscall flow integrity protection, or shortly SFIP. This is a novel idea that complements the control flow integrity with integrity for user-to-kernel transitions. So SFIP would extract the allowed syscall transitions in an application to construct what we call a syscall state machine. And then, for example, here, from the application code, we might be able to know that the read syscall will only, the open syscall will only be followed by the read syscall. And then at application runtime, we will enforce such transitions, which means if we're seeing a read after an open, we know, okay, and this is in the application code, it's good. But if we're seeing a write, we know that the application code will not have a write directly after an open, which means there's something wrong, so we just reject the syscall. In the original paper, the authors proposed the implementation for extracting the syscall transitions and construct the syscall machine. And they also proposed the enforcement implementation in the kernel, which requires you to modify the kernel to get this thing to work. But if we're using eBPF, the SFIP will just work out of the box. We can just construct the syscall state machine as an eBPF map, and then we can use Seccomp to enforce the policy. So I hope at this point I've already convinced you that Seccomp eBPF is useful and it has a lot of use cases. Because of the time limit, I will not be able to go over all the use cases here, but I'm willing to discuss about it after my talk. So now let's take a look at how can we make Seccomp eBPF secure. We believe that security it's not obscure, but with systematic analysis and design, we can actually make Seccomp eBPF secure. So my talk will discuss the security in three aspects: the security model, the support for eBPF Seccomp filters under privileged eBPF, and finally, I want to talk about the potential IMA integration to enhance security. So our principle is to reduce the security of Seccomp eBPF to the security of Seccomp and the eBPF subsystems. So in this way, the resulting implementation is as secure as the existing Seccomp and eBPF. For Seccomp, the security is ensured by requiring privileges for filter installation. Namely, this requires either you have capsys admin or the no-new privs attribute is set on the process, so that only in this way can you install a Seccomp filter. And the security of eBPF it's achieved by the internal verification and the privileges for program loading and helper accesses. In Seccomp eBPF, we just maintain all of these security enforcements. So let's take a closer look on how we reduce to eBPF security. And for the verifier, we didn't touch it, so it's always kept the same. And then for the privileges and for loading an eBPF program, this mostly concerns about the context access and the touch point. So this is already covered by the security of Seccomp because Seccomp eBPF, it uses the same context and the same attach point as Seccomp CBPF. For the helpers, we're just keeping the same privilege requirement. This means basic helpers like map helpers are still unprivileged, and then tracing helpers, those from BPF tracing funk proto, will still require cap BPF and cap perf mount. For maps and eBPF, as far as I know, it currently does not have a privilege requirement for maps. But if restricting map usage is desired, we actually added a new verifier hook to restrict the map usage. And in recent years, as we all know, there have been several instances of security-related bugs in eBPF being discovered. This prompted the community to discourage unprivileged eBPF and moving to a privileged-only security model. So what I want to stress here is that Seccomp eBPF will still be useful under privileged eBPF. This is because a lot of virtualization applications, they just run as root by default. So they are still privileged enough to utilize the eBPF Seccomp filters. And in our implementation, we added support to allow users to optionally disable unprivileged eBPF filters based on the BPF unpriv default off configuration in the kernel. And if the unprivileged eBPF are disabled, then we're requiring the same privilege as the eBPF tracing program types. And this is because eBPF filters are similar to tracing programs in many ways. And for example, they share the common set of helpers. They can both changing the function return value and altering the process behavior. So the last aspect I want to discuss here is a potential security support from IMA. So if we can verify that an eBPF Seccomp filter comes from a trusted source, it will always be secure to use it in the kernel. So this essentially turns the security problem into a trust problem. The AMA subsystem in Linux, it checks the signatures of files and verifies whether it comes from a trusted source. So the idea would be implementing AMA signature support for eBPF filters. And then the good news is that the AMA community, as far as I know, are very welcome to the eBPF signature support. And then for more about this, you can refer to KP's talk, which is just right before mine. All right, so let's take a quick look at our eBPF Seccomp filter support. Our patch is based on Dylan's patch in 2018. We added a new program type in eBPF, which is specific for Seccomp. We keep the same attach point and context as the CBPF filters. And then we implemented those verifier hooks that ensures the correct access to the context, and also it listed a set of helpers for the eBPF filters to use. And then for security model, as we discussed before, we're reducing to the security of Seccomp and eBPF. I also want to show you how Seccomp eBPF can be easily integrated into current container runtimes. So the support is implemented in crun, which is a fast OCI complaint runtime, and it's a default runtime for Podman. And we got our support from our collaborator Giuseppe and from Red Hat. If you want to use crun and Podman with eBPF filter, you can just use a command like this, which uses annotation to specify a Seccomp eBPF filter. So to conclude, there had been a lot of discussions on porting eBPF to Seccomp. So here we revisit the Seccomp eBPF filters to see how using eBPF in Seccomp could significantly improve the programmability of system call security in Linux. We identified several real-world use cases that is that can only be implemented using eBPF filters. And we believe that the security of Seccomp eBPF can be ensured with a well-defined security model. And then lastly, you are very welcome to check our code in our GitHub repo. So that concludes my talk. Thank you. And any questions?
So I think this is super cool. The Seccomp BPF stuff has been going on. I have one question. You showed on one of the slides that there is this exec VE hook, and this is where you stop program executions and you count them. Is that like, is that, why not consider BPF LSM? Because you also need to have exec VE at here. Otherwise, people will just use exec VE at to do the executions. So this is the fundamental issue I have with Seccomp. But I do see the power that all container runtimes are already integrated with Seccomp. So it can have better adoption if you have like Seccomp plus eBPF rather than just BPF LSM. If you could contrast these two approaches, that would be nice as well.
Unfortunately, not too familiar with BPF LSM.
Yeah, so the point was, when we were having discussions about BPF LSM, the idea was either we do Seccomp eBPF privileged, or we hook a layer below the syscall surface, and we provide these policies at like below the syscall layer, so that if one new syscall appears, you will still catch these features. Otherwise, the new syscall is just a gaping security hole that you forgot to attach a filter to. So you would rather attach one layer below and have it as an LSM hook. So why do container runtimes not write a BPF LSM policy rather than using Seccomp eBPF policy? Yes.
I guess. And another point is Seccomp is still, even if you do eBPF, there's those pointers arguments that are fundamentally unsupportable. Right? Yeah. So what's the point of all that? If the next step is to port. Yes.
Exactly. Yeah.
Sorry, I think I missed the question.
So if you convert this Seccomp to eBPF, the natural continuation of this work is let's support the pointer arguments, right? Which we cannot really support because of time of check, time of use. And it's all kind of, you get back to why not just do it like a layer below at LSM level.
Okay. So actually, I have a question on the LSM implementation. Is that like syscall implementation for using BPF LSM?
This is the biggest adoption challenge, right? Which LSM hook is called when what syscall is used? The BPF LSM hook or the LSM hook for exec is called BPRM check security. Why? I don't know. Like, because the structure is called Linux bin PRM. So the adoption story becomes complicated. And this is where I think Seccomp has the advantage in the sense that users interact with syscalls and they know about the syscalls really well. So that's where they want to have a policy. But that's not the right place to have a policy as the way it is implemented currently in the kernel. Because of talk to racism, you will have a new syscall that could do the same thing. So I think the real benefit here is to improve the usability story of BPF LSM rather than like have something built on top of Seccomp.
Okay,
Yeah,
so
I think
that one of the concerns is because when we have a new syscall, we'll escape the security policy, right? So actually, for Seccomp, it is recommended to implement your filter as a blacklist, so that when there is a new syscall, it will not just magically escape your security policy. It will always be blocked.
Yeah, I think Seccomp was originally designed just as an attack surface reduction mechanism and grew quite a bit from there. And the real need for a lot of the container runtimes and other things is much more like the mandatory access control that the LSM layer provides. But there wasn't anything that could be installed by the regular user. It was, everything up until about a year ago had to be installed by the system owner, not by some program. You install Chrome, how do you get the new policy you want installed into SE Linux or AppArmor or whatever. Landlock as an LSM is providing a closer confinement than these other things, and it's been designed from the perspective of being unprivileged. And sort of the standing problem that exists with the eBPF stuff is that privilege boundary. Even with BPF LSM, it's expected to be run privileged, and even this Seccomp eBPF is sort of presented as needing to be run privileged, but the real need is for even unprivileged to run, and I think that LSM layer gets you much closer to the confinement level that you want, and Landlock is working on that right now.
I think I think Landlock is super cool. Like, it allows an application to protect itself, right? From a container manager perspective, where somebody is running at a privilege, where it can install policies, like as this slide mentions, I feel that there is a use case for the BPF LSM like policy to ship with the container itself. And if they need deep argument inspection and complicated policies, this could be implemented in BPF LSM. Stanislav just mentioned that there is support for C group based BPF LSM policies, which like fits right into the container ecosystem. But there is, I do agree that there is work in order for people to use BPF LSM, they need to understand what these hooks are. And I, for myself, find it hard sometimes to understand them. So anything that we can do to map syscalls to various LSM hooks is the way this could work. Seccomp, otherwise, you will run into the same issues we've been talking over and over again for the last 10 years, I would say.
So
any other questions, comments? Yeah, go ahead.
Yeah, I was just saying, could you be more clear about like what issue the Seccomp is having, like in the last 10 years?
So, like, if you read the discussions that have happened here, right? One is the surface it attaches to. It is above, so you can solve that with a denialist. But the main issue that Stanislav mentioned is talk to, right? The time of check, time of use race. So even if you implement deep argument inspection in Seccomp, which you really want to, if you want to do complicated policies like these, that's the next logical step you will end up with, and then you will realize, I'm at the wrong surface in the kernel, and you don't want that.
Okay, I see your point. Yeah.
All right. Oh, one more. Okay.
Yeah, I think the layer issue is LSM is going to be a better place to catch those things to avoid all the race conditions, and that's sort of understood. And then the privilege issue is solved by Landlock, and then the mapping of hook to what does it mean is actually also solved by Landlock, because it was the same complaint as like, how do I expose this in a meaningful way? And so Landlock said, okay, here's the specific policy and what it means, and then internally that maps to the hooks, and that's what has to evolve and not the policy language. Landlock still needs a bunch more coverage. It has a pretty narrow use case currently, and I think that's the problem, is there's a lot of these overlapping solutions that don't quite answer everything, and that is frustrating. But I think that if we could get to the point where we could have something like Unveil, as you know, is done in by other operating systems, it would be really nice, and we could actually use that for normal processes, for container runtimes, for everything. But right now, neither the LSM nor Seccomp is really in a good place to do that. But I hope for.
So I think the kind of use cases the person who was presenting mentioned, like, this should be doable with the BPF LSM, right? Exec ones, state machine transitions from one syscall to the other. This should all be doable with the BPF LSM. So I would encourage you to prototype that. One interesting thing you brought up in the slide was the signature stuff. Like, if you say that only packages can ship with signed programs and the whole distro ships with the signature policy, and those can be installed, maybe you can allow BPF programs, signed programs, to be installed by a privileged installer process that has some security attribute that allows it to do that.
Yeah, and I thought once we have the signature, we can also and it potentially allowed unprivileged BPF Seccomp filters, right? Because we know that, okay, those filters are coming from a trusted source. So IMA is protecting me from being, attacked.
Yep, nobody's going to write a speculative side channel gadget, and if you try to authorize one with BPF, then it's up to you to live with ramifications of that. So it does need some thought, careful thought, though. It's just this thought of unprivileged BPF scares me, even with signature packing it.
Okay.
All right. Thank you, Jinghao.
Thank you.
All right, the next talk by Jerry about K-probes, trampolines, batch attachment.
Okay, hi everybody. My name is Ilya. I work for HID-BPF. This presentation is about the current status of batch attachment for K-probes and trampolines. This is kind of long ongoing work, but there has been some progress. So basically I will sum up what's done and what actually still needs to be done. So batch attachment, basically we want to speed up attachment of BPF programs. If you have a BPF program and you want to attach it to thousands of functions through K-probe or BPF trampoline, that's what we're trying to provide API to make it fast. Basically, you need the API because at the moment there was no suitable API for that, and in addition to the API, also the BPF program needs to have way to find out, because now the BPF program is executed from multiple functions. So it needs to find out which function actually triggered the BPF program, and it needs to have a way to access the arguments for the BPF program. So basically we ended up having new helpers for that, which will give you these values. And also there's a possibility for each symbol or address to add user value. User can specify the pointer of user data for each IP address, and that can be retrieved by the BPF program when it's executed. So basically that's what we need for batch attachment, the API that will do it in a fast way, and some support in the BPF program. So it all started a long time ago. I started adding the support for BPF trampolines, but it turned out it needed a lot of preparation works. And at some point, I was actually asked how it would look like for K-probe. And it turned out that it would be much faster to do, and there would be maybe even bigger benefit. So all the work, I actually took the K-probe detour and made it available for detour. So I will describe how it works for K-probe, which is actually the support is already merged, and then I will describe where we are with the BPF trampolines. So K-probe as such is quite generic interface. It allows you to add probe almost everywhere in the system. So there are there is this API register K-probe where you say where you pass the K-probe object, where you specify which address, and it's not really attach friendly interface, multi-attach friendly interface. Because when I actually started to adding the possibilities to add like multiple symbols to the K-probe, it was denied, like maintainers didn't want to touch this interface. And also based on the discussions, it turned out that when you want to attach to thousands of functions, you don't want this generic functionality that you are able to attach in the middle of the functions. Basically, when you want to attach to thousands of functions, you are interested just on the entry of the function. And that actually, that was the breakout here, because K-probe as such, when you place it on the entry of the functions, the attach layer for that is ftrace. So K-probe subsystem is using ftrace to actually attach the function. And when we got the ftrace involved, it was basically the win, because ftrace allows you to attach to almost all the functions in the kernel, and it can do it very fast. And it's already running the K-probe programs, so there's no problem even there. So how it actually looks like, you have a function, and from the profile call in the function, there's a special ftrace ops hook, which is executed when the function is executed. And this hook is actually calling the K-probe callbacks, like the pre-handler and post-handler. I was actually, some of those preparation part sets that I sent was actually to add multiple symbols to the K-probe object, but that was denied. And after discussions, Masami added the new probe. It's called fprobe, and it's basically wrapper API for ftrace function tracer. It's based on ftrace. It's the wrapper, so it's very multi-IP attach friendly, and yeah, it's using the ftrace. So ftrace takes the addresses or symbols and attach the hook and calls the hook, and also adds the multiplexing. So if there's like other tracers attached to the functions that they are attaching to, it will actually manage that everything gets executed. So this is like this is a new interface that's easy to use. Register fprobe, and you can pass the addresses or the symbols, or even like a regular expression that's understood by the ftrace. And yeah, basically it looks like the K-probe on the entry. The only difference is that each fprobe is having their own ftrace ops object, which its own fprobe handler, and this fprobe handler will call the entry and the exit handler, which is specified in the fprobe object. So with this, we had actually the way to attach, to have the callbacks from multiple functions. So the only thing that we had to add was the interface between the user that would actually register all the functions and the BPF program together. So there's new link, BPF link. It's called K-probe Multi, and it uses fprobe as attach layer, and it does the connection between the, like, it provides the user interface to actually connect all those functions to the program. This is the same picture as for fprobe. The only difference is that K-probe multi-link is actually providing its own handler, and this handler is called for every function, and it's actually executing the BPF program. So that's like the whole execution path.
How does the interface looks like? So on the kernel side, it's new link. So there's been like addition to the BPF link create command. So there's new structure, kprobe multi, where you can specify all the symbol, all the addresses, or the addresses, and you can specify cookies, which are the user data for each symbol or the address. It's existing link create command, so the BPF program actually is like the FD field in that attribute. So that's on the kernel side. On the LibBPF side, there's similar addition for the BPF link rate. So you can use it like this. You provide the program FD, say that do you want to use the BPF kprobe multilink, and in the options there's new structure where you can actually specify all the symbols or the addresses or the cookies. And there's one more extra function, BPF program attach kprobe multi options, which basically do the same on higher level. You can specify the program, the BPF program. You can also specify like the regular expression for the functions that you want to attach. If you don't specify that, you can use the options, which are basically, again, the same. You can specify symbols or addresses and optionally the cookies for each address. And yeah, I said it's based on ftrace, so it's fast. We actually have even self-tests that will read the ftrace file, which gives you like all the functions that are traceable in the system, and we will attach like simple program to all those functions, and we measure how fast we can do that. So in this setup, you can see like almost 50,000 functions we were able to attach in less than 1 second. So thank you, ftrace. It works and it's fast. Who is actually using it at the moment? So these are users that I'm aware of. BPF trace was like the initial implementation, like the support in BPF trace I was using to actually test the feature. There's support for Tetragon in the form of pull requests at the moment, because we are waiting for the eBPF library to actually merge the support for multiple kprobes. And there's pull requests that actually adding the kprobe, multiple kprobe support for the Tetragon. Red Snoop is using that, as far as I know, and based on the questions that I'm getting on the chats, there are probably also other users. So it's being used. So that was the success part of the presentation. Now, trampoline badge attachment, which is still ongoing effort. Basically, what we outlined some time ago, what we need to do is like to have a way to have generic trampoline, so to be able to create trampoline that can be called from multiple functions, and this trampoline must provide the programs the ability to get the argument values, to get the IPs, while being executed from different functions. Then the actual interface that is attaching trampolines to the functions was slow, because it was designed just to attach one function, so we needed enhancement in that. And as it turned out, something that I call mixing trampolines is causing troubles at the moment. So yeah, those first two bullets, actually, they're done and merged, and I will be discussing the next one. So quickly about the generic trampoline. So trampoline is now generated in a way that it can, when it's called from multiple sides, like from multiple functions, the program inside the trampoline can actually get the information about the arguments and can get information about the IP address and can get the cookies. So basically, we can use the trampoline that we have at the moment, and we don't need any other special trampoline. The ftrace direct API, so that's something that we use when we have the trampoline and we want to attach it to the function. So this is like the current interface. It looks like there's just a single IP address and the address of the BPF trampoline. So if you want to attach like thousands of trampolines, you need like 1,000 times to call a register function. The way the attachment actually works is that from the profile call of the function, like in this example, the schedule, from the profile call, we call directly the trampoline, and the trampoline environment actually expects that. So it actually expects that the register will have the values of what's being called. When we are called into the functions, these register values needs to go to the trampoline image, and of course that includes also the stack. What the direct interface does is it will actually connect the trampoline like this, and if there are other users of that function, other ftrace users of that function, ftrace will run those users first, and then instead of returning back to schedule, it will run the BPF trampoline if there is one attached to the function. So the trampoline will always have this kind of environment, like all the register values that comes to the function. We added a new interface to be able to attach the trampoline to multiple functions in a very fast way. So there are 3 new functions: register, ftrace, direct multi, with the multi suffix, where you say like the ftrace ops object that you can initialize with all the addresses that you want to attach to. So instead of calling like multiple times the previous interface, now we can do it in one call and in a very fast way. So the trampoline can get all the data, and we have a way to attach it in a very fast way. Now, actually, it turned out there's a problem that I call mixing trampolines. So at the moment, the situation looks like this. We support only single trampolines. That means each function can have attached just one trampoline. So there's no mixing. If we add the concept of the multi-trampoline, so say you want one trampoline, BPF trampoline image to serve on multiple functions, you can do that. It will look like that. And if you actually allow this multiple trampoline to mix with the single trampoline that is currently attached, it brings another complexity, and even worse if you want to mix like 2 multi-trampolines together. The complexity comes from the fact that the actual attachment to the function, there can be always just one single trampoline. So if you actually want to mix the trampolines and call multiple functions from 2 trampolines from one function, you actually need to generate one special trampoline that will call all the needed programs, because there will be only one trampoline attached to the function at the time. So in this case, when you have mixed trampolines, the actual attached trampolines on the functions, there will be actually 3 trampolines as a result of mixing those 2 trampolines. So you will have trampoline 1 that needs to call program 2, trampoline 2 that needs to call both programs from both trampolines, and the rest just for program 1 from multiple trampoline 1. And yeah, even worse, if you like keep adding new trampolines, the complexity gets in the same way, and you actually start splitting the trampolines, and yeah. So that's the current problem. It's basically, yeah, it's a problem. I sent a patch set on this, but it was quite complex, and I guess because of that, it didn't get much review. So I actually came back to allow just mixing of multiple and single trampolines, which turned out to be much simpler and manageable. And yeah, so but it all started again in the discussion if we should support also mixing the multi trampolines. So that's basically the current status. And maybe, as I was discussing with Andrew before, the question might be if there is actually need for interface for multi-attaching of the trampolines. At the moment, we have the interface to attach like multiple functions for the cape ropes, and as for Tetragon, that's currently what we need. So also my question would be, what's the real use case? And yeah, with that.
Okay, so I have a comment. Well, first, it's like not exactly clear from your slides, like what's the actual problem, right, of mixing trampolines, besides just like conceptual that you need like to split into multiple subsets. But I know what it is, but like no one else does.
Oh, okay. Yeah, basically, is the complexity of splitting the trampolines. What the first patch said here does you need to create another layer of abstraction, because BPF trampoline comes with the link and is stored in the link. And if there's another trampoline coming and it needs to split existing trampoline, you're actually splitting somebody else's trampoline, and he needs to know about that. So there needs to be like extra layer for that. So that's one problem. Another problem is the locking, which is tricky. Every time you split the trampoline, you need to take the lock for the trampoline. And if you are splitting like hundreds of the trampolines, that can get ugly. And yeah, well, it's implemented in this RFC patch set that I'm mentioning here. And yeah, that was the biggest pain, actually.
So I wonder whether it's possible to have a trampoline of trampolines, so we don't really split the actual trampoline, but have another layer that allows different trampolines to jump back into.
So one other thing that the patch set is actually doing, it's removing the trump links, and it's storing the programs for the trampoline in array. The reason for that is once you split the trampoline, you end up with single program being attached to multiple trampolines. So we needed to store it in a different way. So I'm not sure I answered that.
So if you can go back to like previous slides where you had like those multiple trampolines mixing, right? So like if you have TM1 attached and then you want to attach like single trampoline to function 7, for example, you cannot just attach it to trampoline 1 because it will be also called for function 5, 6, 8, and so on, right? So you need to split the existing trampoline.
Yeah. I mean, to have another layer of trampoline, basically, if you have another trampoline to function 7, that trampoline will be, so everyone will jump to a special trampoline, and that trampoline will be somehow smart enough to get you to first TM1, and you jump to the other one for function 7.
You mean like chaining the trampoline's execution?
Yeah, you have training for the trampoline, but of course it's difficult because you have F entry and F exit. But I think the benefit is like you don't have to have this split. And that may be slow, but I will consider that's a corner case that we're just making it work. But it's slow is okay.
But this would probably not work for exit handlers, right? Because the trampoline is actually calling the...
But wouldn't this require to create multiple trampolines, one trampoline for each function? Like from the very beginning. So like, let's say we have nothing attached. Now we try to attach TM1. Like it seems like what you're proposing is to have like trampoline for function 3 and then separate trampoline for function 4 and so on, which will eventually call into TM1, right? Just so that you shouldn't split afterwards. So like that, even if it's like not slow, it's just memory hungry.
I don't think we need a separate trampoline for each function, but we need probably a execution plan or something. It's like lookup table, say where you want to go. It will be slow, but
I don't think it will be slow. So slow is not an issue here. But Song, what you're proposing like totally makes sense, except for the case when the trampoline is calling a regional function. If you have two trampolines, both of them potentially will call a regional function twice. And will be like really hard. So what you're proposing, like it works and brilliantly and like avoids all the complexity that GD hit, but it only works for F entry. For F moderate, it's not clear which one you would be modifying because you need to like transfer the value, the return value from this nested trampoline somewhere to the other one. And that's where it gets the same level of complexity.
yeah, so I had that problem in mind. I haven't think about whether it is, I was under the impression that it's probably possible to hack through, but I'm not sure. I may be wrong. You probably thought about it thoroughly and think it's impossible.
So just what you're saying, initial knob will jump to an image that will be more jumps into different trampoline images, different trampoline locations, or is that?
Yeah, something like that.
So
you have
knob, jump, and then call to this image and then call to the other image, like, and then back here and then call and then back here.
Yeah, something like you probably go back after F entry, call the function, and then go back to. You got multiple F entry trampolines. You go through all of them, then you.
Yeah, you will need. Yeah, it will get a bit messy. So yeah. Try to get it.
Yes, it's just actually. What about we have two separate trampolines for F entry ones and F exit ones?
F moderates.
Yeah. Well.
I think it's like not that hard to split conceptually, right? And like even with locks, you can order them by address, like take all of them. Like this is like not a super fast, in the sense like we don't call like thousands of times per second like multi-attached, right? Like one of the problems was that you have like one link keeps one trampoline. That was the problem. So like splitting like trampoline afterwards for some other link was the problem, right?
Yeah.
So like one way to solve that would be like that we have one trampoline that has multiple images, and then images can be attached to multiple subsets of functions, right? That way, like you don't have to modify original links and just original trampolines, but that's fine because like you need to log them
basically
anyway.
that's what implemented like in the multi part set that I sent. Yeah, but it brings it.
As to like you were asking about the the need for this, right? Like I see two advantages to that. First, like it's slightly faster than kprobe, right? In terms of like invocation of that. And second, and that was kind of original motivation, is that like you have fexit, which has input arguments stored, right? So like there might be use cases where you want to capture generically like input arguments in fexit. I don't have those use cases right now, but like that's just one of the advantage, right?
Right.
And there is a question on the chat, right? Question, if an ftrace hook has multiple trampolines, are those trampolines called from a wrapper function or mixing trampoline code into one?
Say it again.
I can read it again. Yes, I didn't get it. If ftrace hook has a multiple trampolines, are those trampolines called from a wrapper function or mixing trampoline code into one?
So ftrace, it's important to know that the trampoline, the BPF trampoline, is executed after ftrace does everything. And ftrace, if there are multiple functions attached to ftrace, there's like, it will execute them before the BPF trampoline gets executed. There's only one BPF trampoline linked to the function. There's like, you cannot have like, say to the ftrace attach multiple BPF trampolines to one single function. It's always just one.
I'll ask this regardless. This is a separate law.
So this direct ftrace thing where the ftrace does its business and then it goes to BPF directly, the ftrace maintainers are not very keen on porting this to other architectures, I would say. So they and they're mostly like, this was a thing that they shouldn't have done on x86 rather. So have you run into any of these conversations with the ftrace folks? And if Steve is here in the audience, he could answer this as well.
Not really. Yeah, I think Steven wasn't happy about adding that interface, but I didn't hear any other complaint about it.
So the thing is that what they want to do is they want to make this BPF trampoline and ftrace op as well, right? And I think that has this extra register. I mean, this is what Floro has been working on, and this has this extra register saving that happens as a result of that, and that is less performant, but that needs to be proven. So, and this is what effectively blocks the current BPF support for ARM trampolines.
All right.
Yeah. So we should do a BOF of this and get some clarity on this as well. Are we as BPF okay with it being an op on at least ARM, or is ftrace okay with providing like a ftrace direct support for ARM?
Right.
I'll throw another question into this. How hard would you think it would be to implement multi-attach uprobe?
Right. Yeah, I don't know much about the uprobe. So.
I think that would like immediately benefit both BPF trace and Red Snoop, right? Like there are use cases where, especially like think about USDT, for example. USDT is actually one-to-many mappings. Like one USDT is potentially many different places in the user space process. So supporting USDT efficiently requires multi-uprobe, apart from all other use cases. So
we were very lucky in the kprobe side that it was actually running on the ftrace. If it wasn't, I don't think we would be this fast with the implementation. But it was based on the ftrace, and ftrace does all the hard work here. So I'm not sure how uprobe is implemented, and probably all depends on that.
Yeah. So I have a question about how this, even let's say we solve the split part. I think from the ftrace part, we cannot do the atomic switch, right? Say initially we only have one one single attach. There's a direct function. We have to switch that direct function, to another direct function, right? Oh, and I don't think like ftrace support, you switch from one direct to another. You only have modified the call address.
The interface is basically, yeah, you always attach one trampoline to one function, and that's it. It doesn't allow any other setup.
The concern is atomicity.
Right.
Yeah, so there is no, so like this trampoline like doesn't add anything new, it doesn't make anything worse, it doesn't make anything better. Like from the ftrace side, the attachment is not atomic to multiple.
So I think what Song is actually worried about is like if we had like this multi-trampoline attached to like function 7 and others, right? And then we want to attach something else for function 7, right? Like will we be able to atomically switch to a new trampoline, new image for function 7? And I think yes, because that's how like the current trampoline works, right? Like you can update the image and then swap it. No?
No, so you have, say you have two functions, one already attached to, one trampoline attached to function 1 and 2, and you want to attach another one just to function 2. And from ftrace point of view, that will be two separate direct calls. They will be separate. There's no longer one multi-ftrace, multi-direct ftrace ops. But that switch will not be atomic, meaning we may miss a middle event in between. And that's how we were missing event for the one already attached before, and that one is not expecting to lose event.
You can expect regardless because of multiple CPUs and everything.
No, but that if that's the case, that would mean that like when you have attached fentry and fexit, and you attached fentry to some function, and then you attach an fexit program to the same function, then we can lose fentry call. Is that the case today? I don't think so. It is? No. It's about swapping image, not the trampoline, right? And like from ftrace, it's just like atomic switch for that particular function. So I think that's fine. It's like one pointer, right? So like we swap one pointer basically.
No, but initially you have function 1 and 2, they are sharing the same pointer. But later, if you attach another trampoline to function 2 only, they will have two different pointers.
So like the way to do that, like one way to do this would be like you create a new trampoline that has function, like one program call and another program call to function 2, right? So like you have a new trampoline that calls 2 BPF programs for one function, and then like for function 2 you just swap it, and whatever was attached to function 1 stays attached with the original trampoline. As Jiri said, it's complicated. It's kind of, yeah. So we are running way out of time, but we have break as well, so we can take it offline. Thank you, Jiri. We'll be back in 20 minutes.
So the main thing, like what you think you were asking, like whether it was finishing? Yes, definitely was finishing. I think like he give it the guidance why it makes sense to finish. So it's like just splitting doesn't sound as bad.
Yeah, no, it's
and also you can also do like what I was proposing, just doing one trampoline action measurement. I think it's better to have a feature than optimizing that not just different features for attachment. Like instead of splitting it, you say like attach 1000, just straight
But same program would actually no, I don't even try the HID-BPF. Like cash for sure, but not like to make it easier.
So what if we do trampoline? Trampoline stays the same, but we have a list of images associated with this trampoline. And then we split like that list.
Yeah.
And then locking, like what's the problem with locking? You just like take, like you find all the trampolines that you need to split things up, right? You lock all of them in like predefined order by atlas. So like it's always defined what kind of you don't mind it. That's it, then you split. And splitting you do like also, you have sorted atlases and just like intersections. Obviously it's not, you know, it's elementary, but
2021.
that's how you did it. Yeah, so that's different from what I keep striking the other track. I say what's talk to you about internal
I think it will be. So, what do you think of having a graphication where you don't have variables? And then treat it like
just replace one with none.
in that project, then and it's high we get yes, so moderatory before, I mean, therefore we don't address in the just distance. Yes, actually, so one thing I didn't yes, that we use in also, but there's been a series of suggested to have multi. So, and then the way they work is they have a shadow stack, and so the based on the rules before the function, you can see on this shadow stack, and then the red I don't know where they are. For example, I set the looking still. So does it sound
as long as we have like the arguments of the
yeah, it's like yeah.
Oh, did someone download it like literally 5 minutes? What? Maybe it's or maybe twice.
Then we have actually to check what is the effect of
But 41? That's what I'm saying.
So you compare it as a feature. Yeah.
Right, just no work. There we go.
So on Microsoft concept, double
check that. Is that right? I know. It's actually the agenda. Don't worry, I might just. I just changed. Yes, perfect. So it's building doesn't work. Yeah, don't. It's very uniquely priced. Yeah. We need to ask them.
I mean, it's fine. I wasn't getting this to move forward. I still do some stuff on the FSC side, but yeah, it's fine. To me, it's okay. Yeah. Yeah, I think we label some stuff, but then we get
Every item, I don't what is the question? I think it's hours just when you go. Yeah, I think it's 1 hour. I think it's fine. Don't worry. I mean, I'll be here. You can tell. You're gonna be. You and I are gonna be like moving slides. Yeah. Cool. Like, so we'll see that. Yeah. I think it's fine. We're gonna print it, right? Oh yeah. Because we have PC. Yeah, but yeah, sure. Yeah. That works. Yeah, it's not.
Well, I think I tried
I'll give everyone one moment. Is it Javier?
Yes.
And Vaishali?
Yeah, Vaishali.
All right, folks, let's get started.
Yeah, you're right. Yeah, no, you're right, you're right. Do I look okay?
All right, so the next talk is by Vaishali and Javier about developing BPF profilers for polyglot cloud native applications.
Yeah, so hi, it has been a long day, I guess, but I hope we are able to keep you all engaging for the next few minutes at least. So yeah, we are going to talk about developing eBPF profilers for polyglot cloud native applications.
Yeah, well, my name is Javier, and I'm a software engineer at Polar Signals, and I've been working on this thing we're going to talk about today that is mostly focused on unwinding native stacks.
Yeah, so before we dive more into our talk, we wanted to talk a bit about today's agenda. So we want to talk a bit about what we mean by profilers and especially what we mean by infrastructure-wide profilers. Then we want to talk a bit more about like the low-level ecosystem we are leveraging, for example, like the debugging formats, elves, and dwarfs. Then we want to talk a bit more about how stack unwinding and walking is being done in the Linux kernel, especially, and please keep in mind that generally industry uses like stack walking and stack unwinding interchangeably, but most of the time when profilers are using it, it's mostly just stack walking because we are not really deleting any frames or we are not really changing it. We are just reading those data. And then we want to talk a bit more.
Yeah, we're going to be talking about how to build profilers using BPF and why this is a good idea. We're going to spend a good chunk of that also describing how to walk user stacks without frame pointers, because this is a big problem in the industry, I would say. And then we will talk about some of the future work that we want to do, as well as some time for questions.
Yeah, so let's talk about profilers for the cloud native environment. So generally, as we all know, like developer machines and the production environments are not similar. Most of the time they differ in, of course, like in the specs, but also sometimes in the OS, ARC level, etc. And with the rise of like container technologies, especially Kubernetes, we have kept adding layers and layers. So now it's like hard to manage the resource usage for servers and the host systems. And small variations in the software that we run between our development environment and production can have a big difference where our bottlenecks lie. So profilers help us to pick into the resource usage like CPU, memory allocations, heap, I/O, etc. Most common type is the CPU profiler, which helps us to, that's like the amount of time the CPU spends executing particular piece of code. There are two main types of profilers, like tracing and sampling. For the scope of this talk, we will be talking about sampling profilers. Raw data for the sampling profilers are generally stack traces, as well as like the values attached to those stack traces. So we'll be talking about a bit more about like the generic approach when it comes to the profiler model, but we'll mostly be talking about what we are doing. So there might be different components which other people are using over there. So first, generally, we have to decide what we want to profile. So most of the time, there is some sort of discovery mechanism we need for the targets. We want to either profile certain section of the processes via PIDs or C groups, etc. In the traditional profilers, people use signal handlers for that. Most times with infra-wide profilers, it's nice if we can profile every process. And that's also like sort of the model we are using in our profiler, Parka agent. Once we have discovered what we want to profile, sorry, it's, oh, now it's so, yeah, so once we have discovered what we want to profile, we need a mechanism to collect the stack traces. Generally, this mechanism involves at two levels. We want to collect the stack traces at kernel and then the application like user space level. And generally, these stack traces have IDs, memory addresses, etc. Once we have collected this stack traces, we have different formats to use. Most commonly used one is BPF, which was created by Google. It's both a format and a tool chain to visualize and analyze profiling data. And it has like different metadata components like samples, locations, mappings, functions, etc. And once we have that, we need to symbolize it. Symbolization is generally the technique that allows you to translate like machine memory addresses to the human readable function names, etc., line numbers, symbol information. And again, that also happens at two level, kernel and application. Different ways, there are different ways to symbolize it, but mostly the process involves like reading symbols from, say, .debug info files, or like in the case of kernel, we have proc or syms. There are also like remote servers like debug info D, where one can find debug symbols extracted from libraries and objects. And last but not least, we need to visualize this data in some or other way. Usually it's being done in the industry with the help of flame graphs and icicle graphs. Today we will be mostly focusing on the part where we are collecting the stack traces and stack walking in this cycle. So before we dive more into specific details about like how we are using eBPF for developing these profilers, we need to understand a certain foundational low-level technologies like the debugging formats. Also, please keep in mind that we are mostly talking about x86, 64, so some of these details can be different for the ARM or other architectures as well. So ELF and dwarfs. So there are different debugging formats. They are like hidden and obscure component of our computing infrastructure used by performance analysis tools, debuggers. It knows the state of the stack. Generally, compiler knows the state of the stack every point in the function, and it can output it in the different sections. For example, ESFrame or debug info, etc. Another widely used format is dwarf, which is a bit more complex than ELF. It has like the basic descriptive entry called common information entry, which has like different sections and opcodes. There are different tools which are being used to read this information at the moment, like readelf, optdump, all of them have like different options. One of the one which we use very commonly and we really like is the readelf, and a lot of different options from them. So what does this stack traces look like? So for example, when C code calls another function, the call instruction pushes the return address onto the stack before branching into the callee function's code. In order to create a stack trace that's human readable, one needs to find each return address, look up the function associated with each one, and print each function name in the sequence. However, functions use stack space for other purposes. Most commonly, like to store the previous value for the callee save register, or to store the value of the local variable. Each function's stack space can be accordingly different. Like the size of the stack frame can be accordingly different. So it's difficult to know how many bytes are between each return address. Like I have shown into a small image in the x86-64 ABI specification. There are different registers called RBP, RSP, etc., which we'll talk about in the next slide. So to get the stack trace, the first thing we need to know is the current program counter. Now this is found in a CPU register called RIP, instruction pointer register, and it points to another region of the memory that holds the executable machine code of our program. But as mentioned, the variable length of the stack frame is hard to determine, and this is where the frame pointers come in. So a frame pointer is a register which always contains the previous value of the stack pointer. And on x86-64, the register in question is usually RBP. So frame pointers are generally used for stack walking. We start with RBP, then we continue dereferencing memory until we reach the bottom frame. In the process, we collect the return addresses for the functions. But there are certain pros and cons of keeping frame pointers in your binary. Many distributions and packages actually disable them for the performance gain. If we use RBP for the stack unwinding, it's one less registers that we can use for our code. And potentially more data will be spilled to the stack. This is not much of a problem when it's like 64 bits, but especially for the 32 bits, there aren't many registers. So it was used to be, or it's still a real performance problem in that sense. We add 3 instructions to set up the preamble epilogue. So not only they have to be executed, but they increase the executable size as well, resulting in reduced instruction cache hits. So what are the cons of disabling frame pointers, and is it still worth doing? So walking the stack becomes orders of magnitude more expensive, of course. Instead of involving a couple of machine addresses per frame, which is quite fast, we will have to do more work, especially in the unwinder. Debug information of some kind of is required, but sometimes this unwind information is not correct, and it results into the inaccurate stacks because of the different format and how this information is being saved. Without frame pointers, the compilers or some part of the toolchain generates actually extra data, and this is more work that the compiler has to do. Writing correct unwind information is very difficult as the different compiler passes, linkers, etc. need to keep them in the sync, and this is also sometimes case for the subtle bugs. Plus, the unwind information can be huge, and then the accuracy we have to determine and we have to test more, etc. Sometimes almost as big as like executable itself. So what's the reality of the industry at the moment? If you're a hyperscaler, it's fine, because in Google or Meta, most of the time, this code is compiled with frame pointers. It's great as a debugger profiler implementer, because it means that the walking the stack is very easy and computationally cheap, of course. But the real reason why developers keep it is when you are under the pressure, you need the reliable and fast stack traces, which is like must. But the harsh reality of the industry is that most of the engineering community elsewhere is not compiling all their software from scratch, or they are not really using the compilation options that doesn't keep the frame pointers. For example, GCC has the option to omit the frame pointers, which is used by most of the binaries. Like OpenJDK has an option to preserve the frame pointers, which means that by default, it doesn't have the frame pointer. One of the reasons we have come across why many packagers don't enable this feature is because their worries are about like the performance penalty, etc., but also about the competition. And you have to sort of really users need to know why this performance gain or loss is worth it or not. One important point to also remember here is that even if you compile your application's code with frame pointers, it's not enough, because every single library that is dynamically linked with it also needs to be compiled with frame pointers, and libc for most distribution isn't compiled with frame pointers. So is this worth it or not? But there are also some frame pointer believers. For example, Golang after 1.7 version, they have always been keeping the frame pointers. Mac OS software is always compiled with frame pointers. We don't know when they started doing it. The Linux kernel is also compiled with frame pointers. But there is an interesting exception, which we'll talk about in a bit. But basically, there's a config option to not use them. When this option is selected, unwind tables are generated and added to the kernel image. Then whenever the stack trace is requested for, like, say, kernel profiling, live patching, etc., the stack can be unwound using the method that's being chosen at the compile time. And this is like props to a good work by org developers. Fun fact, though, kernel's just-in-time compiled code, eBPF, is also actually using frame pointers. This is all great and fine, but of course, this doesn't cover everything. What do we do if you want to profile any process running on the Linux box, no matter the runtime, no matter how it's compiled? How can we do this?
Cool. So as Vaishali said, let's see some of the techniques that are used in the kernel to unwind the stack when there's no frame pointers, as well as some of the work that we're doing right now to make this work for user space as well. So first, let's take a look at the kernel. So the kernel by default uses frame pointers, but in x86-64, there's this option that you can enable a compile time. When it is enabled, it will generate these unwind tables that are inserted in a custom ELF section. And this doesn't rely on dwarf or debug frame or EH frame. So it is way simpler and faster and uses way less CPU. The cool thing about this is that the kernel mechanisms are completely abstracted away. So whenever you call any API to walk the stack, it just calls the right backend, which has been selected at compile time. Cool. So some languages, like, for example, C++ have exceptions, right? So how does this work? Like, if there's no frame pointers, when there's an exception that is raised, we need to unwind it, but how does this work underneath? So turns out compilers like GCC and Clang generate information in the form of dwarf debug information, so the stack can be unwound without them. So as Vaishali was saying before, we need to figure out what is basically the value of the stack pointer before the function started being called, so for the previous frame. So these unwind tables could potentially be synthesized from the object code, and this is the approach that actually org uses. It partially disassembles the code from the kernel and generates these tables. This is very interesting, and is something that we might do in the future, but so far we have chosen to go for the dwarf approach. There's some other creative approaches that some people do, especially when you have to debug under pressure. You have no debug info, no frame pointer. So one approach that I find it interesting, but obviously we're not doing because it's a heuristic, is to dump the whole stack and find what are the values that look like they could be return addresses. So at the moment, we rely on dwarf debug information. So let's take a look at how this works. So here we're using readelf to dump this table for this test program. And here we can see the table for one function. This function has 4 program counters, which are on the left. And then we have 3 other columns. The first column tells us how to find the stack pointer for the previous frame. The second one tells us where to find RBP. And the last one tells us where to find the return address. This table is completely generic and has information about any register, because any register could be pushed in the stack. But this is important because this mechanism is so flexible that, in fact, in Dwarf, it is implemented by, well, you need to implement a VM and decode a state machine to be able to actually generate that table. So with this flag in readelf, we can tap the opcodes and the effect that executing these opcodes have. So for example, you can see the opcode advanced location that basically sets a new program counter, and the opcode of the family offset, such as def, CFA offset, and offsets, which, for example, in the first case, show that in order to calculate the stack pointer for the previous frame, we need to get RBP and subtract 16 bytes. So adding a small VM implementation in BPF is something that could be potentially very daunting, and we want to avoid for many, many reasons. But fortunately, we can take advantage of 2 insights that work for this particular case. The first insight is that we only need to restore 3 pointers, which are the stack pointer, RBP, and we need to find the return address. And the other one is that our trade-offs are very different to, for example, what the C++ unwind mechanism trade-offs or what a debugger decides is more important to do. So usually the way they work is they are lazy, so they only find the unwind information for the program counters they need, because there's not that many program counters they need to unwind. In our case, it's a bit different. We want to have a continuous profiler that runs all the time. So the cardinality of the program counters is going to be very high. In our case, we generate the tables ahead of time, cache them, and only update some metadata of them. So for example, we can generate them for every single executable, and if they are a dynamic library, we can update the address where they have been loaded. So it's kind of a little bit like a relocation, if you will. So yeah, first let's take a look about how to walk native stack traces in BPF with frame pointers. It takes 1 line. Obviously, there's a lot of work done by the BPF developers to make this happen. And in reality, it's 2 lines. We need another one to define the user stacks map, and then this one to fetch the stack trace. We get a stack ID, which is a hash of the addresses. And once we have this, we could, for example, send it to user space using a perf map, ring buffer, or we could aggregate it directly in user space. And this is actually what we do. We keep a count of how many times we have seen each unique stack trace. And every couple seconds, we gather these statistics, we generate some profiles, we reset these, and we get another set of profiles sometime later. Let's talk about how to do this without frame pointers. Sorry, didn't work. Cool. How to do this without frame pointers. So our current implementation is a bit more complex than the previous one. It is 250 lines of C code, obviously without comments or spaces. And the dwarf unwind information parser and evaluator is more than 1,000 lines of Go code. This doesn't account for tests, doesn't account for any other architecture but x86-64, and doesn't account for other sections. Right now, we only support frame. So as you can see, like just in terms of number of lines, it's slightly more complex than when you have frame pointers. First, let's take a look a little bit about the architecture. Like, it looks like any other BPF application, really. We have 2 main components. We have the driver program. In this case, we use Go because we were already using Go. That takes care of BPF program and map lifecycle. So it creates the maps, the programs, loads them, attaches them, etc. And from time to time, it reads some input from them. Then on the BPF side, we have a map which contains, well, we have several maps, but this is the most important one for us, which is a mapping of the process ID to an unwind table. And then the BPF program that is knows how to unwind the stack using these tables. Of course, an important component here is in user space, the unwind table generation. So the unwind table is built up with a bunch of unwind rows, and these unwind rows have two main pieces of information. One of them is the program counter, and the other ones tell us how to restore RSP and RBP. Right now, we are omitting the return address because we have hard-coded it. We know that at least in x86-64 is 8 bytes ahead of the previous stack pointer, so we haven't implemented that. But there's a lot of things here that in the future we might have to reevaluate. One of the things that we definitely want to do is we know there's some ways to make this a bit more compact, and we'll talk about this later in the future work. So the process we follow here is first we have to find the section. We use some ELF parser, and once we find the section we want, in this case we only focus on EH frame. Later on we'll have to do debug frame, which is similar but has some subtle differences. We're gonna find, once we parse, information for every single compile unit, and within every single compile unit there is data for every single function, and then for every single function we have a bunch of dwarf opcodes waiting to be evaluated. Once we evaluate them, we have around, by the way, like 30 plus opcodes, I think. We'll get a table that basically for every single program counter in the program tells us how to restore the registers. Cool, so in the BPF program, we basically have to do these operations. First, we need to find the unwind table for the current process ID, and then we do the stack unwinding. It's kind of a classic stack unwinding. While main is not reached, we know main because we are passing it to the BPF program, like the low PC and high PC. We append the program counter to the stack. Then we find the unwind row for the current program counter, and then we restore the registers. We need RIP, RSP, and RBP. RSP and RBP are needed because the unwind row has information on how to find the previous RSP, sometimes based on RSP or based on RBP. So once we finish this process, we should have stack trace. So yeah, we have to obviously do this efficiently, and the obvious way here is by using binary search, which is interesting to implement in BPF. And the good thing about having this data already sorted is that we can, of course, remove redundant rows. So sometimes for program counters that are adjacent, we have exactly the same information on how to restore the registers because they are not they don't change. So by doing this in some tests, we have saved around 10 to 15% of the entries in the table. So this is an excerpt of the BPF unwinder. This is only the function that takes care of finding, of doing the binary search and finding the actual unwind row. It's not very complex. It's your standard binary search, but I just showed it here to show some code from our BPF unwinder, and also to talk about like two things we had to deal with, right? So when you're writing BPF programs, one of the most fun parts is to deal with the verifier, and there's like some easy things. Like in this case, we had to double check that all the accesses, all the pointer dereferences were checked. So we were not dereferencing like a null pointer, and that all the arrays, all the array accesses were, not out of bounds. But then the more interesting ones was that the BPF verifier checks, symbolically executes all the code paths that your program could have. And for our simple binary search, not this one that we're showing, but the previous iteration, it was complaining that it was hitting 1 million of symbolic instructions that it had analyzed. The problem was that we tried to reduce the amount of iteration that this unrolled loop was doing, and the verifier was happy doing 7 iterations of less, and 2 to the power of 7 is not enough. So we need at least 15 or 16 iterations. So the current workaround that we have is that we use BPF loop, which is very, very new, but it's amazing. But of course, we want to support older kernels. There's some people that use our open source product, and they run very old kernels that have BPF tail calls, but not BPF loop. So yeah, there's quite a bit of stuff to keep us busy. So we want to test all this implementation in bigger real-life binaries. So far, we have done this work on small self-contained binaries, and this worked so far. But I want to make sure that it works on any application. So for example, something that we need to work on, we already fixed a lot of bugs here, is on the table generation, right? It's easy to not implement some opcode properly or not implementing it at all, and then your table will be completely off. We only support x86-64, but of course, there's a lot of people in the cloud that are running ARM64, so we want to run that in the feature as well, at that feature. And an important thing is that the table size is static. We have an upper limit of 130,000 entries, which is enough for big applications such as the C Python interpreter. But some other applications that people run will use way more entries. And we need to do a lot more testing, and we want to engage with different communities because we think that this is an industry-wide problem that is worth fixing. So happy to take any questions, and of course, to talk with you in the hallway track.
Well, one comment actually. Join the fight. We are proposing for Fedora to build everything by default with frame pointers. So.
Hi, it's a good presentation. It's interesting about you put the whole the frame information into the BPF in the map, right? So how many is this? How is the size of your information?
Yeah, so I had way more detail to talk about, but I was being told that we were over time. So some of the approaches right now, we only have 130,000 items, rows that we can put in this table. And we know that we will need way more for some other binaries. So the idea we have is, of course, to split it in chunks, to shard it, if you will. And one of the most obvious things that we want to do here is shard by build ID. So have the different, like, for example, dynamic libraries in their own kind of table. Still, probably for some big binaries, we'll have to split a single binary into several tables. So we'll probably have two levels of binary search, one to find which BPF map is the one to use, and then once we find that one, within that table, right? But yeah, this is something that we're going to be working on in the next couple months. And by the way, everything's going to be open source. So yeah, like we hope to release this soon.
Hi. Where can I get where can I get a source code of your implementation?
Yeah, so our project is open source, but this implementation hasn't landed yet. But our project is called Parka Agent. If you look it up on Google or GitHub, it should show up. But right now, it only supports binaries compiled with frame pointers. This is something that will hopefully land in some weeks.
There is a comment in the chat. For everyone interested in profiling, there is hotel approach to unifying the industry. Open telemetry profiling region. I don't know. Check the chat. There is a link.
You guys are using perf events under the hood to gather the stacks, right? Have you considered using LBR to help you unwind?
Sorry, which thing?
The Intel last branch record.
Oh, yeah, but the problem is that in cloud environments, it's not always, well, as far as I know, it's almost never virtualized. That's a problem. Some of the people run AMD and yeah. So the problem we have here is that we want to have some solution that works for the bigger set of users, and there's many of them that don't have them available. Yeah.
Gotcha.
Yeah, so as I said, I think like the only like really production, like general production approach is like to compile everything with frame pointer. That's why like we are proposing for Fedora to do it like by default. It's obviously a lot of people have preconceptions how big of a performance hit it is, which it's not. Like there is some noticeable slowdown in some applications, but like it's 0.2% or something. So yeah. As I said, join the fight.
I mean, we are obviously like.
Yeah, so that is from the application to application, right?
Yeah.
And that's often not.
Yeah, but you also have to do a proper benchmarking.
Yes.
You know? There were some cases when like it was benchmarked with frame pointers in debug mode versus production mode without frame pointers. So like there were like 1,000 percent difference or something.
But yeah, of course, like we believe that frame pointers will be like the best thing to have, right? Like I used to work in an environment where everything was compiled with frame pointers and it was amazing. But even if Fedora decides to do this, which I hope they will, what about all the other distros? What about all the other code that is running that is not going to be updated? So
one step at a time, exactly. I would say. Someone has to start.
Yes, I agree. Yeah.
All right. Thank you very much. We are out of time. Thanks for great presentation.
Mm-hmm.
Is it online presentation?
Seems so. Okay, wait.
Okay, so the last presentation for today, because one of the presentations has to be canceled because presenter couldn't make it. So the last one is performance insights into eBPF step by step by Dmitry. Dmitry, go.
Yep. Hi everyone. Well, apparently, I hope you can hear me. Nice.
Yeah, we can.
Although I have some echo, but it's probably going to be okay. So yeah, I'm Dimitri. Yay, the last talk for today. I hope you still have some amount of energy. That's probably one of the advantages of presenting remotely. I don't see how many of you are actually falling asleep already. I would definitely do this actually. So yeah. The context is essentially, we're going to talk about BPF performance, and the context is that at the beginning of this year, I took on a very interesting challenge, part of which was try to get visibility into certain BPF applications that were incorporated into one system. This turns out to be very interesting, and the findings were interesting enough, so I decided to share it and see what everybody thinks about this. Well, essentially, the story goes like this. So normally, when we reason about performance of various applications, everything is relatively straightforward from the visibility point of view. So we have our user space application. This user space application relies to a certain degree on some kernel features, and you know that you could profile stuff, both user space and kernel space. You know which metrics are relevant in every situation, which metrics to collect, and so on, obviously bearing certain complexity and so on. But now the thing is that as soon as we try to, as many projects already doing today, as soon as we try to extend the situation with BPF programs, things are actually getting a little bit more tricky. And for me, it was actually quite interesting when I was starting it sort of like from the scratch, that there was no definitive guide how to actually evaluate or how to even reason about BPF programs performance, which probably assumes that probably assumes that you could already take existing strategies to do this, which was actually not always the case. That's why I decided to jump on it, and you actually may ask why do we even have to be bothering about this? Because BPF, they are extremely small and they have to be also blazingly fast, and you would be actually right, but we're talking here about such projects like, for example, security projects like StackRox, where essentially those BPF programs, they are lying on the hot path of the execution, unfortunately. Which means that even from the many points of view, like even from the strategical point of view, it makes sense to understand what's going on inside, because even the smallest overhead is going to be accumulating over the time, obviously. So having this in mind, I wanted essentially I wanted to do two things. First of all, I wanted to do some sort of a summary. What is actually common ground? What is the state of things, and what is important to understand, which features are important that are affecting performance of BPF programs. And the second more important question was actually which methods and which approaches could we apply, like that we know from the regular performance analysis, which of them and how could we apply to analyze performance of BPF programs. So having those two topics in mind, let's go forward. The first one is the current state of things. Most likely, you know almost everything out of it. It's just a summary, which I find from one point of view useful, and at the same time, some of those we're going to use as an example in the future slides. So The examples are, for example, you need to understand that there are various instruction sets, and you better be using actually the latest supported on your platform, because then essentially layout of your BPF program is going to be as optimal as possible to this point. And yeah, it's just essentially going to be smaller and much more efficient. I'm not going to really spend a lot of time on this because, yeah, there are more interesting stuff in the few following slides. But another very interesting stuff and very practical, actually, it's a batching of the operation. So if you know that you are working a lot with BPF maps, if you do lookups or deletes or whatever with a lot of elements, you can actually, it just makes sense to batch operations to cut a little bit on the overhead, especially if you communicate a lot between user and kernel space. Another very interesting example, it's one of those examples where you're actually not looking at, for example, front-end bound programs versus back-end program and so on. It's an example where you could optimize using even like when you can optimize application algorithmical part of things. So, for example, Bloom filters, which is absolutely mind-blowing thing when you can create a probabilistic data structure that will allow you for a certain particular use case optimize things. It's essentially a probabilistic data structure like it's a BPF map that is a probabilistic data structure under the hood that allows you to figure out if some particular element is not present in the map extremely efficiently. And another one, which we are going to talk about a little bit later, is, and this feature I'm pretty excited about, actually, it's a program pack allocator, which essentially tries to do a very simple thing. It tries to pack all the small programs, BPF programs, together on either normal or huge page so that it will be essentially hitting less. It will produce less instruction TLB pressure, but there's a little bit more to it in a sense, like in a consumption way, which I'm going to talk about a little bit later. And another one is, which is also very exciting and interesting, is, for example, when you know that your BPF program is actually hitting quite often, for example, memory misses or something like that, like cache misses, you know that you always have on the table task local storage, where you essentially could put some bits of whatever you're working with closer, like in the memory, in the area of memory, closer to the actual task you're working with. So those are essentially like a short summary, extremely short summary of what you probably may need to look at when you're developing something new to get actually, to squeeze out some extra performance, some extra efficiency out of already efficient implementation. So now let's talk a little bit something more interesting. So which methods that we already know about, which of the normal performance analysis methods could be applied in terms of BPF? So the first one, and it's actually very interesting, even before running everything, we could already start thinking about this stuff. We can actually start talking to the compiler. Normally, pretty much all the major compilers can provide some amount of performance optimization reports that they were able to produce and performance optimization that we're not able to take. So the opportunities that were actually missing on the table. And fortunately for us, we could do the very same thing with BPF. So LLVM for CLAN compiler has some amount of such options. A couple of them are on the slides. And another very interesting practical thing I found when I was trying to get this report analysis for our particular project we were working with was that actually vast majority of such not taken opportunities were about not eliminating some particular loads. So essentially global value numbering paths were complaining about this quite often. And it turns out, well, to my understanding, it happens because BPF programs are quite often working with this, with this opaque pointers, like, for example, context or something where essentially a compiler doesn't have enough information about what is actually behind this pointer. And essentially this not taking optimization means that compiler thinks that there is possibly some opportunity to take, but compiler doesn't have enough information to actually do this step because maybe the validity of the program is going to be compromised in this case. A very interesting situation, and even more interesting to see that some of those not taking opportunities I was able to eliminate in our particular case by just playing around with the restrict keyword, which is a very simple thing. It's just a keyword that allows you to give more information to the compiler. It essentially says that there are no overlapping pointers that are going to be overlapping with this particular one. So essentially you can say that there is no memory, that there are no pointers, either derived from this one or directly this one could be updated from the outside, which sometimes makes sense. And just even such a simple example like this already was able to eliminate some amount of those not-taken opportunities. So now let's go a little bit further, and now we're already running some stuff. The first very simple thing when we try to analyze performance is actually to get some global statistics. So for example, uptime or load averages or something like that. So for BPF, we could actually do something similar. So we could essentially check out the global statistics that kernel collects for us when we enable this actually. So for whatever reason, it's not always enabled as far as I understand. But this is it's not very detailed information, but at the same time, it's very simple to get it. And at the same time, it provides you some sort of like really interesting and simple ballpark numbers for, for doing, for example, sanity checks for other methods, more advanced methods. Another also sort of hilarious approach that it's still, I decided to put it on the slides because people are still doing this and it's pretty much visible everywhere. You could literally modify your BPF programs to actually print out something on using printk, which is of course not efficient and you're going to do a lot of overhead, so it's not feasible when you have a lot of events, but still sometimes very simple approach, very flexible, so why not? Now we're coming to something more interesting. So one of the very powerful performance analysis approach is a top-down analysis. I'm not sure if everybody aware about this, so I'll try to summarize it in a couple of words. It's actually a huge topic on its own, but essentially it's about collecting some hardware counters while executing your programs, some certain hardware counters to try to understand where exactly bottleneck lies in your program, and you try to categorize those events in the certain categories. For example, you can say that your program on the first level of top-down, you can say that your program is front-end bound mostly, or back-end bound, or like, for example, there's a branch mass prediction, or essentially maybe it could be that almost everything is actually retired micro operations, which is fine. And then on the first level, you're going deeper. That's why it's called top-down. And then you're going deeper and you're figuring out, okay, maybe our program is back-end bound, maybe the ESB cache is not used efficiently, and so on and so forth. So a very powerful approach because it gives you some sort of a systematical approach to things. Could we apply the very same method for BPF in case of BPF programs? It turns out to be yes. And for that, essentially, so in theory, just abstractly, we could actually do this thing just using event-effective programs. So we create just like instrumentational event-effective program for whatever counters we want to collect. And then we attach them and essentially doing this snapshot at the beginning of the BPF program and at the end, and then compare whatever we want. That was pretty much interesting to realize, especially since everything's already there. So perfstat could essentially provide you this amount of event filtered by some particular BPF program, and it already has first level of top-down method implemented in it. So I was pretty much excited about it, but unfortunately, I'm not sure why, but for whatever reason, I didn't manage to make it work. I was tracing it down to the point that essentially all the counters that I was creating, they were always zero and not a single event was counted. So I was completely confused about this. Maybe something was wrong about my setup. So what I have done eventually, I just extended BPF tool profile command with subset of those top-down events taken from perf, and actually this thing was working. So in theory, it's possible to collect and to apply this approach, which is very, very great news for us. So yeah, about perf, if you know about this topic better, let me know. Maybe there are some particular things that I have missed. So why it's so important that we could actually apply this approach? Let's jump a little bit back and talk a bit about program pack allocator. So I'm not sure how exactly folks came up with this idea that there is, for example, on some particular system and there is a lot of instruction TLB pressure on it, but using top-down approach, you can actually try to figure this out without having a huge amount of practical experience or without some hunch. You just could do this in a more methodical way. So what I'm talking about here is essentially when you see that, instruction TLB pressure usually represents itself when your program is quite front-end bound. So it's one of the contributing factors. And in generally, front-end bounded programs, it could happen that BPF programs could be like that. It's all about layout of your program. So we often, for example, talk that layout of BPF program has to be optimal. So it has to be small, it has to be aligned, it has to be like the hot path has to be implemented in a fall-through way. So all this stuff usually handled for us by the compiler. It's pretty much simple in this regard. But what program pack allocator takes is it takes this idea a little bit further. It tries to optimize this layout across the several BPF programs, which I find very interesting. And having this approach, so the top-down approach, you can actually take it one step further. So the thing is that quite often BPF projects that are used, for example, at least our that we're using from Falco libraries, they are using essentially there's not a single BPF program that is being responding to some particular events, but rather a call chain of several BPF programs connected via title calls. Which means that at the end of the day, when we're talking about layout of the program, we're not talking about a single program. We're talking about layout of this whole chain, which makes it actually a little bit more complicated. And packing them together makes things a little bit already more efficient, but we could take this idea even more further. So let's imagine we have something like this. So we have a couple of memory pages where we pack those programs together. But now imagine that since they are essentially responding to different events and there is this different complication chain of flow, some of them could be cold programs and some of them could be hot programs, so they're getting executed more frequently. And it just happened that just because of the order in which those programs were loaded, it could happen that a couple of hot programs were loaded on the first page together with the cold program, and the same mix and match happened on the second page, which obviously probably not that efficient packing in the regard that you have to take more pages actually to respond to most of the workload. What's interesting is that those BPF programs are actually even small enough so that even like a cache line instruction, cache line size could matter in the sense that, if I recall correctly, BPF programs are located with an alignment that's slightly lower than that. So essentially all those boundaries, when they're stepped over with in the regard of hot and the cold program, they could play a little bit of an overhead, and at the end of the day make your whole call chain a little bit more front-end bounded. So I find that a very fascinating idea. And again, top-down can allow you to think about this in a little bit systematic way. So now let's continue. Usually when we already got some insights that we have acquired from the top-down approach, we know, for example, that we have, for example, back-end bound program because there are some cache misses or something. Usually what follows is that we have to profile our application to understand where is this coming from actually. So where are those hotspots of those events happening and how can we modify our code to actually improve the situation? So the question is again, could we do similar stuff with BPF programs or not? The answer is fortunately yes for us, but there are a couple of caveats that we're probably going to discuss now. So what you could see on the slide is an example of such profiling when I was collecting micro operations retired stalled, which is essentially an event that says that during this particular cycle, not a single micro operation was delivered. And fortunately, this particular BPF program was compiled with BTF, which is just essentially like the best possible situation for us, because now we could actually not only read this output of profile, we could also correlate it with an actual C implementation, which makes things much, much easier. And here we could see that quite a lot of those samples, well, just to make it clear, there were not that many samples, it was just a test, essentially test run. But most of those, well, quite a lot of those samples were actually hotspotting around a helper BPF ring buffer reserve, which probably tell us that we need to look at this deeper and see what's going on there. Maybe it's not really necessary, maybe we can get rid of it, or maybe we replace it with something, and so on and so forth. But one very annoying thing that I find about this is that I haven't actually found any single way how to do this in a more isolated way. So the thing is that when we profile normally our applications, everything is clear. So you just profile this particular thing or this particular process. And guess with BPF, they are essentially they're extending the kernel to a certain degree. And since well, the event could be triggered from pretty much everywhere, at the end of the day, especially on the production systems, you have to profile everything. You could try to minimize this load, by capturing on the kernel stack traces or by trying to reduce it to some particular cores in your machines, but still at the end of the day, you're going to get a lot of unrelevant events, which is quite annoying. So I was thinking, how could we actually filter this out? And I was actually Suddenly, I was pretty excited when I have realized that I could use LPC feature, which is essentially like a sort of a hard way of filtering out some particular stacks that I'm interested in. And it works pretty nicely in many situations. So you can actually profile some certain syscalls if you're interested with that and so on and so forth to get only this batch of information. But my excitement, well, went out quite quickly because it was the second part that I actually didn't manage to make work properly, unfortunately. If you already know something about this, again, let me know. But what happened is that this particular incantation, when we're saying, please record some events, but please filter them out using LPC for this particular BPF program, this essentially fails with an operation not supported, which is interesting because I haven't found any mentioning of not supporting this feature for BPF programs except in the context of virtual machines. So I'm not sure maybe it's deeper than that, but nevertheless, that was a little bit disappointing. So now, one of the probably, well, in this context, the last one, but a very, very exciting approach to performance analysis modeling. So what is it all about? Essentially, when you, essentially what you're doing here is you're trying to create a simulation program. You're not trying to benchmark something or something of this sort. You just create a simulation program that represents to some certain degree that captures the basic feature of your application. And then you run this simulation and see which insights you can collect from it. And I'm mentioning it here because I'm completely convinced that it's actually very important to do this especially in case of BPF, because overall the system is extremely complicated. So you could see that there are a lot of different options to choose, a lot of different maps, a lot of different configurations, memory locations. There could be some cores involved, like inter-core communication. And at the end of the day, this whole system turns out to be a complex system, not in the sense that it's like an intrication of some sort and so on, but in a scientific sense. So the output of our system depends on the input, unfortunately not linearly. At the end of the day, it means that when we try to reason about these models in a more intuitive way, our results could be quite often not correct, because there could be some counterintuitive situations, especially in the case of there are some edge cases and so on. That's why it's very important to try to build such models and see what insights are they providing. So an example that I did for this particular talk, I took a run queue slower from the kernel set, from the kernel project, from the repository, and especially I was concentrating myself on this particular commit when run queue slower was switched from the normal hash maps to task local storage, which was very interesting to see what would be the difference actually. I was actually not modeling it directly. I was modeling essentially the only one particular difference. I was leaving latency the same, but when hash maps are growing, they're usually getting less efficient. That's a very known fact. And task local storage in this regard is supposed to be a little bit more constant. So that was the only difference that I have encoded in my modeling, my simulation application. And then at the end of the day, it was like essentially a state machine where every state was corresponding to a certain process state, it's been waiting on the queue, or it's been executing, or it's been dequeued. And there were a couple of extra situations around BPF programs that are instrumenting queue and waiting time. And here is a small result out of it. Again, the program was extremely simple. It was capturing only basics, so contention of the cores, number of CPUs, or which exactly, is it a hash map or task local storage and so on. And what happens here is that we have by x-axis, we have a number of processes executing in our simulated system. And here we could see an overhead in a percent, overhead in a sense, how much time we spend doing BPF bookkeeping versus how much time we spend actually executing processes. And you can see that the amount of time the amount of overhead we have at the beginning is very negligible. But as soon as we get into the hundreds and thousands of processes, the simulated system is getting overwhelmed. And what's more interesting to see that even with this small difference that I have implemented in the application, task local storage is still much more, visibly more performant than its hash map counterpart. So this is very interesting and very exciting way to try to also get some understanding and try to get insights into your applications. So that's pretty much it. I actually didn't talk about some other approaches because partial lack of time, partially because I still haven't tried them out yet in practice. But nevertheless, I hope that now you get better, or at least you get better, or even maybe potentially new perspective, how to look at your BPF programs, and hopefully you can apply this in the field. And I hope there are some questions in the audience. Any questions?
Anyone?
Oh, hello. Thanks for the presentation. I haven't, I don't think you've, well, it wasn't clear to me whether you've looked at the BPF tool profile feature that can profile particular BPF program with a set of BPF programs and extract like counters, like
yeah, of course.
cache misses, etc.
Yes, absolutely. So that was one of the parts. I didn't put it into the slide because it was sort of obvious, because we can find it in pretty much every manual. And to my understanding, I mean, I'm not sure what is the common consensus here, but to my understanding, people are trying to keep BPF tool a little bit free of the unnecessary stuff. So that, for example, top-down approach, I guess, is not going to land there at all, especially since it's implemented in Perl. So that's why I not put it in the slide directly. But yeah, that's one of the things that I was using quite often during this whole investigation process.
Cool, thanks.
And one thing that I haven't seen, and maybe you can tell more, this restricted pointer. Is it about like pointer aliasing, right? Is it really doing something, or I guess compiler can in most cases figure it out?
Yeah, in most cases, compiler is actually good enough indeed. The only reason why I started to look at this was that when I compiled relatively simple set of props, so those Falco libraries, I've got literally 6,000 of complainings from the compiler that some loads were not able to eliminate. That compiler was not eliminated to those loads. And to be honest, not all of them are actually handled by this restricted keyword, only like a couple of hundreds probably. So it's like small fractions of those, but still in some certain case, it just makes sense to provide more information to the compiler. Compiler is definitely has a lot of its compilers are quite smart, but still there are edge cases when some extra information could help.
Interesting. I want to sprinkle some of them in our programs and see what happens.
Yeah, try it out. I'm not saying that it's going to be like extremely helpful, but again, just enable those optimization reports and see what will be the result.
Yeah, so it wasn't clear to me, like when you added restrict, like what actually improved? Like what are we improving here?
Oh yeah, sorry. So I probably wasn't clear about this. So what was improving is that compiler was able to do its job more aggressively, and some duplicated loads. So essentially the memory or like the values that are getting loaded or some registers that are getting probably duplicated and they could be deduced from before that. Those loads were eliminated, and essentially at the end of the day, it means that your program is getting a little bit less backend bounded because there are just simply less loads.
Basically, so it eliminated some unnecessary reads of the context fields. Exactly. Is that right? Okay. Any other questions?
So earlier you mentioned that you dumped some of the LLVM optimization passes to figure out what was missed. Did you try this also on more complex applications? And if so, what did you find specifically that for optimization?
Yeah, so in fact, I was trying it on the most complex stuff that I was having, essentially on this BPF side of things, which is sort of a derived, which is a fork from the Falco libraries. And its complication comes from this graph approach. So it's just a bunch of various BPF programs connected together by themselves. They're not really complicated. They're not really big. They're just, collecting some information and storing it somewhere. So that was the top complication I was able to get my hands on. So probably if you have some different type of BPF programs, maybe you'll get something different. But as I said before, the most of the, literally vast majority of reports were about those missed opportunities, about the duplicated loads. There were a couple of more reports. I actually don't remember exactly what was it about, but they were, maybe a couple of hundreds of extra reports of some other types. So they were not really catching my attention in this regard.
Also, I probably missed it as well, but you had this slide where you said you use parf -- top down. I'm first time seeing that. What is that? Can you explain what it does? Maybe you have example output of that or something? So you said like you couldn't make it work, right? But like what you expected to get.
So let me put it this way. I couldn't manage to make it work for BPF case. Normally, of course, it works. So this.
Yeah. So the question is like when it works, right? Like for normal applications or kernel, I don't know. What do you get with top down?
So what you get is a very nice output where essentially you see that you see a report that during this execution we have collected this and that many events, and out of those events we are managed to conclude that your program is, for example, 30% front-end bound. What does it mean? You have to check it out, the definition of those front-end bound events that are like falling into this category, and then you have to start profiling for those events to see where they're coming from. Or you see that, for example, the program is back-end bound 60% of the time, and then you have to think about memory management for your program. So you essentially see in which category your program is falling just based on those events. And then stepping on the second level. So unfortunately, Perf does not support the second or anything below first level. So stepping down with, for example, other tools that supports this, you can go up to the second level, the third level, up to, I believe there are 6 of them or so, and you can narrow down this point, what is exactly bottlenecking your application. So that's essentially the output of this tool.
Okay. I never knew about this. Probably should try it. So like Perf basically tries to help you understand like where your bottleneck is.
Exactly. So normally you have to get some sort of experience. Normally you need to understand what's going on, or maybe like a hunch. Aha, my application is probably has a lot of TLB misses or something. And in this regard, Perf just tries to help you in this regard to like replace this hunch part.
All right. Cool. Any other comments, questions? Well, I guess this is it. Thank you very much for the presentation, and we'll be wrapping up for today. All right, folks. We'll see you tomorrow, I hope.
Talk about what? Rust and BPF?
All right, so Sangre is reminding us that there is like another talk about writing BPF programs with Rust or something like that. So Rust and BPF, if you're interested in either. In the Rust micro conference, yeah. Use this opportunity.